Just imagine deploying a complete production grade microservices system where every code push automatically updates to your Kubernetes cluster with zero manual intervention. And that's exactly what we are building today using GitOps. So hello everyone, welcome back to DevOps Talk. In today's video, we are going to deploy a production grade GitOps driven microservices application on Kubernetes, which is a complete setup that closely mirrors how real-world DevOps teams build and manage scalable systems. And this project is based on a microservices architecture where multiple independent services work together and each containerized and deployed separately, making the system more scalable, resilient, and easy to manage. We'll be implementing GitOps using ArgoCD, where your Git repository acts as a single source of truth. Any change you push to your Git is automatically detected and deployed to the cluster. So there will be no manual kubectl commands needed. Along with that, this project also demonstrates a complete DevOps ecosystem, including CI/CD automation, containerization, Kubernetes orchestration, and production level best practices. And by the end of this video, you will not only deploy the application but also understand how modern production systems are designed, automated, and continuously delivered. So if you are preparing for DevOps roles or want hands-on experience with real-world projects, this video is going to be extremely valuable for you. So let's get started. So before we jump into the deployment, let me quickly show you the architecture of this project so you understand how everything's connect. So before showing you the project architecture, I'll show you the application architecture of it. This is the application architecture. So this is a type of e-commerce platform, but unlike Amazon type stores, it focuses on curated products, a limited collection, and strong brand identity. Think of this is a digital version of a small fashion store. But from technical perspective, this is a modern boutique app which is based on microservices, not as a single application. You might know what is microservices. I'll tell in a shorter way. Microservices is an architecture style where an application is broken into small and independent services, and each services handles a specific business function, and it runs independently and it communicates via APIs, right? Like how we have multiple microservices: front end, checkout, shipping, currency. These are different microservices, and they communicate via APIs. Every microservices can communicate via APIs and they runs independent. So instead of a one big application which we call monolithic application, we have multiple small services working together. So this is a boutique app, like boutique e-commerce application. And we have multiple services such as cart service, then order service, front end service, shipping service. So these many services we have, and all, as I said, these services are communicated using gRPC, which is faster internal communication. So I'll give the service by service breakdown. So this cart service, it has a persistent which is Redis, and it used to store cart items and the product IDs. Why we have Redis here? Because it is fast, simple, and easy to reset. So in Kubernetes, it will run as a pod or stateful set. And then we have this checkout service. So there is no dedicated database for this checkout. It aggregates data from card service, payment service, and shipping service, and it simulates the order placement. It does not persist any orders, right? So only the cart has the persistence. So by design, this application itself kept it lightweight so that you can deploy it easily. Then we have product catalog service, which is this one, product catalog service. So as a catalog, it stores the product as a static JSON file. It loaded into memory at startup, so there will be no DB, no database for the product catalog. Then we have recommendation service. So it is stateless. It generates the recommendation dynamically. Then we have this payment service. So there will be no storage for payment service, and it creates a fake payment processor, which is fine for our demo application. Then we have shipping service. So there will be no storage for the shipping service, and it simulates the shipping cost logic. Then we have email service. So there will be no storage for email. It just prints the logs that email has been sent. Then we have add service. So again, there will be no storage for add service. Then we have front end. So front end is our stateless application. It just provides the UI and API calls to every services. You can see, right, these API calls are connected to checkout, then shipping, currency, card. Then we have currency service. It's a static exchange rates, and it stores the data inside in-memory database. So there will be no separate database for currency. And one more thing has left out, which is load generator. We'll see what is load generator and what it is doing in that application cluster. We'll see this at the end when we'll see scalability and all. So this demo intentionally keeps most services stateless to simplify deployment and focus on platform concerns like CI/CD, observability, scaling, and networking. So we'll understand all this in this project. So this is the application architecture, how different services connects to each other and how they call the APIs. So this is the application architecture. Let's see the project architecture. And this is the project architecture which I built. So initially we'll deploy the infra using Terraform, right? So we'll be using AWS, and we'll be using EKS to deploy the application. So first in our local machine, we'll install Terraform. Then using Terraform, we'll deploy the infrastructure like VPC, and then subnets, and these subnets, internet gateway, NAT gateway, Bastion host. So whatever infra we are seeing here, Route 53, SCM, whatever infra we are seeing here, we'll be creating it using Terraform. And Terraform state file will be stored in a S3 bucket. So we'll be using remote backend for Terraform. Alright, then this EKS cluster is a private cluster. I mean, the control plane is managed by AWS, but the node group are in private subnet, and this is public access disabled. So no one in the public, or no one in the internet can access this EKS cluster. So to access that, we need a Bastion host. So using Bastion host, we first, from our local machine, we first SSH into our Bastion host, and from Bastion host we can manage our cluster, and that Bastion host will be in the public subnet. So this is clear. So initially what we'll do, we'll, in our local machine, we'll install Terraform, and using Terraform, I'll definitely explain every Terraform code, each and every line I'll explain. And we'll be using remote backend as S3 bucket in the Terraform. And once our infrastructure is ready, we'll SSH into Bastion host, and through Bastion host we will manage our EKS cluster, and we will manage everything inside our private subnet. All right, then we have, in the node group we have two instances, and inside the two instances we have all our workloads. I'll come to this part. So once our infra ready, this part is done. I mean, infrastructure is ready, and then public subnet, private subnet, internet gateway, NAT gateway, subnets, route tables, everything we managed using Terraform, including Bastion host. Then we'll move to our CI part. And one more thing, in the Bastion host we'll be installing Helm, we'll be installing kubectl, AWS CLI, will configure those here, and through this we'll manage our EKS cluster. And if I talk about the CI part, from our local machine, we'll push that code to our GitHub repository. So we have multiple microservices like cart, catalog. So there are 11 microservices are there. We'll create images using that source code. So basically we have Docker files. I have this GitHub repository here. I'll put it in the description. So in the readme file you can read all of this, whatever I explained. You can read all this. I have like step by step explained everything in the readme file. You can go here, and here if I go to my sources directory, and here you can see every services has their source code in the src directory. If you go inside that, you will be finding a Docker file. That means we can build images using the source code. So once we build the images for every services, we'll push that images to GitHub container registry. Yes, we are not using Docker hub here. We are using GitHub container registry. In the short form, we can call it as GHCR. So we'll push the images to GHCR and we'll push the source code to our GitHub repository. How I pushed everything here, right? And then we'll be using GitHub action. So to use GitHub action, we already have the CI files mentioned here, CI trigger and microservices CI. So once there will be any changes in the SRC directory, this GitHub action automatically triggered and it checks out the code. It then builds it and the tree will scan the image as a CI part. Tree will scan the image and again it will push to GitHub container registry. So initially we pushed that image. Again, when someone will change some code in the SRC directory, the GitHub action will get triggered. Then it will check out that code, it will build and it will scan that image and push again to container registry. Then when this GHCR packages are updated, it will trigger to ArgoCD image updater, which I will show you. Let me explain this first, then I will show you what this ArgoCD image updater does. Let me just zoom in a bit. So here in the cluster, we are using both IAM role as service account and pod identity agent. So first, we'll install a gateway controller, and when you will install a gateway controller, it creates a load balancer, application load balancer. Then we'll use gateway class and gateway, and we'll be using gateway API for that. Once our gateway API is done, then we will be installing ArgoCD to deploy our application. As I told you, we will be using ArgoCD and GitHub Action both. GitHub Action for CI and ArgoCD for continuous delivery. Once ArgoCD is installed, then as a ArgoCD application, we'll deploy our application. I'll explain the code step by step. Just understand the architecture. So our application will be deployed as a ArgoCD application. Once it is deployed, then again we have external DNS. What external DNS does, it automatically whatever host name you are using here, it automatically talks to your DNS zone, which is Route 53, and it updates the record. Let's say you will be exposing your application using hostname app dot something something.com. Then instead of manually updating the records in Route 53, external DNS will update the records automatically. So we'll deploy external DNS, we'll deploy ArgoCD. Once we'll deploy ArgoCD, we'll expose ArgoCD using gateway API. So we'll be creating gateway class, gateway, and LB configuration, HTTP route, so that we can access ArgoCD user interface in the internet. Similarly, we'll expose our application in the internet. So after that, one more thing, external DNS will be using pod identity agent, whereas rest all like Prometheus, Grafana, and other things are like EBS CSI Driver. Those are using IRSA. So now once this is done, we will install ArgoCD image updater. So what ArgoCD image updater does, it will continuously checks the GitHub container registry. We will configure in such a way that it will check if there is any new images has been updated to the container registry packages. If there is any new update, it will take that update and through the API, it will directly edit the manifest in ArgoCD. So the ArgoCD will reconcile everything. Reconcile everything means once the new images has updated in GitHub container registry, it will take that image, it will talk to ArgoCD, and ArgoCD update the application. So this will be completely CI/CD. I mean, this continuous integration and continuous delivery happens. Then later on, and one more thing, here we are using ACM. So when we are configuring our HTTP route or gateway in gateway API, so we will mention the certificate so that we can access the traffic using HTTPS. The client will request HTTP request. It will go to the gateway then further connects to HTTP route. Then based on our routing rule, it goes to the service, and through services it will directly send to that port. I mean, the request is directly sent to that port. So this is how the traffic happens. I mean, from internet to the EKS cluster to that pod. And we have different namespaces here: ArgoCD, logging, then kube system, boutique app, where our application is deployed, then monitoring. So once this application deployment is done, we'll be configuring our monitoring and logging setup. So for monitoring, we'll be using Prometheus, Grafana, and Alertmanager for alerting. In the cluster, Prometheus will take all the metrics, and inside Grafana, we'll use Prometheus as data source, and you can visualize how the things are performing. And if something goes wrong, if we want to set alerts, then we'll using Alertmanager. You can also use in Grafana's inbuilt alert, but here we are using Alertmanager. And through Alertmanager, we will configure Slack. Based on our alert rules, Grafana is configured with Alertmanager, and we will get the alerts in Slack. Similarly, for logging, there will be ECK Operator, who operates Elasticsearch, Kibana, and Filebeat. So we'll configure Filebeat so that it will take logs from our application, and it will send to Elasticsearch. So Elasticsearch will act as a data store here. I mean, a database for logs here. So this connects to EBS CSI Driver. So we will also deploy EBS CSI Driver, so that whenever Elasticsearch needs some storage, it will directly talk to AWS, and AWS will configure one new EBS volume for the Elasticsearch. So all our logs will be stored in EBS volume, and then we'll configure Kibana to fetch all the logs whichever file bit has sent to Elasticsearch. Kibana now will take all the logs, and it will show us in the UI, and we'll expose Kibana using gateway API. So using HTTP route, we'll again expose Kibana, so that from outside we can access Kibana with our domain name. So the flow will be, if a user access our application, let's say HTTPS, again I'll explain. We are using SSL and TLS here, and we'll use ACM certificate. Whenever we'll configure the gateway, we'll configure with this certificate, SCM certificate, and this SCM certificate we create using our domain, Route 53 domain. So whenever a user will try to request our application, let's say app.devops.site, it will go to Route 53, and through Route 53 it will take the certificate, and here in load balancer, so this is the load balancer which the gateway controller created. So from the load balancer, the TLS terminates here, then the raw HTTP traffic will move to gateway API, then through gateway API it will go to boutique app. So the request will go like this: from the user will access the application in the browser, then it will directly go to Route 53, then in Route 53 it will check that, then from the Route 53 it will directly go to the load balancer, then through the load balancer, and in the load balancer, as we are using ALB, so here only it terminates that HTTPS or SSL and TLS, then it send the raw HTTP traffic, and here in the gateway API it will directly send that to the application. Similarly, when the developer and DevOps engineer try to access the ArgoCD, because like normal user doesn't access the ArgoCD, Kibana, Grafana UI, right? So here you will give this domain, you will set up this domain using Route 53. So the developer, whenever the developer wants to see the logs, like logs, Kibana, or the Grafana UI, so they can easily go to ArgoCD and Kibana. So this domain you will provide to developer or other DevOps fellows, right? Prometheus, Grafana, everything is exposed outside. So similarly, this will go to Route 53, then through Route 53 it will go to here load balancer, then through this it will move to Prometheus, ArgoCD, and Kibana. And we don't need to, as I said, we don't need to create the records in Route 53 manually, because we already have external DNS installed in our cluster. So whenever there is a request by gateway API's HTTP route, the external DNS will automatically creates the record to Route 53, and we can access it from outside. And at last we have load generator. So this is the part of this application setup. So this microservice is used to generate traffic, and it then connects to HPA, horizontal pod autoscale. So it observes the scaling behavior and validate reliability. So what this does, this microservice continuously send HTTP traffic to the front end service. So this front end service. So the traffic flow will be load generator to front end. So this HTTP route will send traffic to load generator, and from load generator to the front end service, and front end service again connected to other APIs, right? So why we need this load generator? Because it mimics the production scenario. We'll see how how our application scales. So using this load generator, we'll send HTTP traffic to front end service, and the scaling will be usually applied to front end service, then again cart service, checkout service, other services, whomever is connected to the front end service, and the scaling will apply to those. And then using the horizontal pod autoscaler based on our loads, that app should scale. It helps us to mimic the production scenario and scale our application, which helps us to achieve the scalability and reliability. Right? And one more thing I wanted to tell here, which is this setup. So you might be thinking, why we only managing our application, which is the boutique app e-commerce application, through ArgoCD? Why not this logging and this monitoring setup? Why we are only managing this boutique app through ArgoCD? The reason is, when you are managing it through ArgoCD, so whomever has the ArgoCD access, they can manage the application. Let me put it in a different way. Suppose you created this application as a ArgoCD app. Now, let's say a person named Zone, who has and who is a developer, let's say is a developer. All right. Now he has the UI access of ArgoCD. He can, let's say, as a developer, he want to change something. I mean, he want to see, I push that code into GitHub action. I push that code into GitHub action. And now that continuous integration and continuous delivery should happen, and that John should verify whether that application pod has been picked that latest images. So you deployed your application as an ArgoCD app, and John, who is a developer, who can log into ArgoCD UI and can verify whether the application has picked the right image, right container image, and is running rightly. John has verified it. Now John doesn't need access to your EKS cluster, because he can verify from here. Now John has no idea about the monitoring and the logging part. And you, as a DevOps engineer, as an SRE, you only manage the logging and monitoring inside your EKS cluster. You don't want to give access to Zone for monitoring and logging stack. So for that reason, we are deploying our application as an ArgoCD app, and we are not deploying Kibana, Grafana, or Prometheus through ArgoCD, so that whoever has access to ArgoCD, they can't see these application. We only, as a cluster administrator, Kubernetes cluster user, can manage this. I hope you understood the complete architecture diagram. If you have any doubt, let me know in the comment section. I'll definitely try to clear the doubts. We can come to this architecture diagram any point of time while doing the deployment, and we can again see how things are connected. So as I said, this is the GitHub repository, and here in the readme file I already mentioned the step-by-step introduction. Even I have added that architecture diagram, and implementation also step by step has been added. So now let's dive into the implementation part, where we will see everything whatever I showed you, everything will be seeing from start to end. So let's see the implementation, and let's install Terraform first in our local machine. So we need to install AWS CLI and Terraform. First I'll install AWS CLI. Just search in Google AWS CLI, you will get the link. So then choose the first link, or just simply search Terraform AWS CLI version 2 install. Click on the first link, just scroll down a bit. Here you will find Linux, and these are the commands to install the AWS CLI. I'll copy one by one and paste it over here. Depending on your network speed, it downloads. Let's unzip that zip. Yeah, it has been downloaded. Now let's unzip it and then install it. Okay, it says there is a pre-existing AWS CLI installation, so I already had installed it. So what I can do is I can just update, but in your case when you run this command it will work. Alright, so I'll just do ---- update. Great, it is installed. Let's verify by using AWS ---- version command. Yes, so AWS CLI has been installed. Now let's install Terraform. Click on the first link, and here you will find install using package manager, and just choose Linux. As we are in Ubuntu, so I am choosing Linux. Then in the Ubuntu and Debian version, you can see the installation commands. So I'll just copy and paste one by one. Here you will find a simple copy button. Just click on that to copy and paste one by one. Now let's verify the GPG keys fingerprint. Now let's update. And install Terraform. Alright, it has been installed. Let's verify by using Terraform ---- version. So Terraform is successfully installed. Now as Terraform is installed, let's clone our repository. So as I told you, I already attached this GitHub repository link in the description. You just go and check that out. I'm just gonna clone the repository. Just copy the link and I'll do git clone and paste the repository link over here to clone it. Once you cloned, now cd to that repository or the directory. Now if you do ls, you will find a Terraform folder, which is this one. Just go inside that and let's try to understand what each Terraform file does. So we have Bastion issue2, we have data.tf, we have EKS.tf, we have outputs, then Terraform tf and vpc.tf. Let's understand what each Terraform file does. So I'll open that in VS Code. As I'm using VS Code, so it's similar in Linux and Windows both. So if you are using Windows machine, that is also good. You can implement the same using your Windows machine. If you are using Linux or Ubuntu like me, then you can use that as well, even for Mac. So here I'll go inside Terraform and let's understand. So let's start with terraform.tf, because as you start with Terraform, the first thing first you will implement this file. I mean, you will write this file. So what does this do? So this is the Terraform block, and it defines Terraform setting and the required providers, right? This particular line You write Terraform, then inside that you will write required providers. This tells which provider and plugins are needed. So for example, we are using AWS here, so the provider name, this is the provider name we are using in the configuration, and here in the source we have mentioned HashiCorp/AWS. That means it downloads the AWS provider from the HashiCorp Terraform registry, and here in the version we are specifying the version to lock the AWS provider for version 6.28.0 to avoid compatibility issue. Next is the provider block. This configures how Terraform connect to AWS. Here in provider we have mentioned AWS again. It specifies that we are configuring the AWS provider, and in the region all the resources created by Terraform will be deployed in this particular region, which is US East 1, which is North Virginia. So in simple terms, this block tells Terraform which AWS region to use when you are creating some resources. Now next go to data.tf, and these are the data sources. What exactly is the data sources? So data sources fetch existing information from external provider like AWS or other APIs instead of creating the resources. Let's say you have already a VPC available in your AWS account or AWS North Virginia region, and you want to that VPC to create your subnets or create your resources inside that VPC. To get that VPC ID, you will be using data block. Simple. Now here you are using HTTP data block, which fetches your public IP address from your external API, and this is the particular endpoint which returns your public IP. When you call this, then Terraform gives you your public IP. Let's move to the next data block. This data block finds the latest Ubuntu 22.04 AMI in AWS, as we mentioned over here. So it finds the latest AMI, latest Ubuntu AMI. We are using like multiple filters over here. So this filter matches the name like Ubuntu Jammy 22.04, then it matches the name, and the second one, it ensures the AMI uses the SBM virtualization, which is required for modern issue. Alright, and this is the owner, this is the official owner of Ubuntu, like canonical AWS account ID. It ensures Terraform doesn't pick a malicious community AMI, so it will pick from the official sources. So this is what your data block does. Now let's move to vpc.tf. So I'm going like in a hierarchy, like when you run Terraform first execute this Terraform block, then data.tf, then vpc, then other files, right? So in a hierarchy I'm trying to explain you. So this Terraform code uses the pre-built VPC module to create a networking resources in AWS instead of writing all VPC resources manually. So as you can see, we are using a module here. So this is the already created one which is available in the Terraform registry. We are reusing that. We are not writing anything manually. And this is the community Terraform module, and we will be using that to create complete VPC setup. Here as you see, it declares the module named VPC. Here we are mentioning source. So basically the source is Terraform AWS module, then VPC AWS. So it will pick from the official Terraform registry, which is maintained by HashiCorp, and this module automatically creates VPC, subnet, route tables, internet gateway, NAT gateway, and other network configurations, which saves us time and a lot of efforts, right? This particular block, this is the name for the VPC, and this is the side range of the VPC. And here then we are mentioning the AZIs. Availability zones will be US East 1A, 1B, and 1C. Then we have a private subnets. It creates infrastructure across 3 availability zones in the US East 1 region. So US East 1A, this will create this private subnet. For 1B, this will create this, and for 1C, this will create this particular side range and private subnet. Similarly, for public subnet, we are adding 10.0.101.0/24, and similarly it goes on. So we have 3 private subnets and 3 public subnets. Then we are enabling the NAT gateway, and we are disabling the VPN gateway as we don't require it. If you don't mention explicitly single NAT gateway, then for every private subnet it will deploy multiple NAT gateways. So explicitly I have mentioned the single NAT gateway is equal to true. By default it's set to false. Alright, then map public IP on launch to true. So basically whenever we will create some EC2 instances or other resources, so in the public subnet it will map the public IPs. Then we are adding the tags, which is Terraform, then environment, then this is for EKS ELB, when you will deploy elastic load balancer, whether you will keep it external or internal. So depend on your tag, it creates the load balancer to the appropriate subnets. That's why we are creating these tags for load balancers, and these are very important for the Kubernetes cluster like Amazon EKS. Cool. Let's move to Bastion EC2TF. And this Terraform code creates a secure Bastion host. You can access private infrastructure like your EKS cluster or your worker nodes inside the VPC. So as I mentioned earlier, we'll be creating the EKS cluster in the private subnet so that no one can access it from outside. And we'll also mention that only people from that particular VPC can access the EKS cluster. So we'll make the control plane public endpoint disabled. So for that reason we need a Bastion host, right? As you know, to create EC2 machine in the AWS, you need a key pair, and when you create the EC2 instance in the AWS UI, it automatically gives you the private key so that you can download it. But here in this case, as we are creating it through Terraform, so we have to manually create the private and public key, and we'll keep the private key to ourselves, and we'll attach the public key to the EC2 instance. Very simple. So here this is the algorithm which I am using to create the private key or the key pair, and this is the RSA bits. Now as the the private key and public key get created, then we'll generate the key pair using this public key. So here is the resource for the key pair. Here we are giving a name called Bastion key, and in the public key section we are using TLS private key, then the name is Bastion key, then public key OpenSSH. So the public key we are giving to the key pair, and we will keep the private key to ourselves. So here it outputs that private and public key both, right? Now we'll save the private key locally. So here we are using local file Bastion key private key, and as I said, it outputs public and private key both. So public key we are giving to Bastion host, and private key we are saving it locally, and the file name called bastion key.pem. So when we will run it, you will be seeing, currently you are able to see there is no file called bastion key.pem, right? So when you will be applying this particular file will be get created. So using that key you can access to that Bastion host. Alright, now the security group. So here we are creating the security group for the Bastion host, and we are allowing the 22 port, and we are making sure that this Bastion host can only be accessible from my machine. So and here we are using the data block, you can see. So what it will do is it will open this 22 port, and only in this machine I can access to the Bastion host, no one can access it. So we are ensuring that using security group. And at last we are creating the Bastion host, and we are giving it a name called Bastion host. Then we are from the data block, as I told you, to fetch some existing data we use data block. So we already defined data block in the data.tf, and now we are just referencing it using data.aws-ami ubuntu.id. If you go to data block, you will see the same thing, data aws-ami ubuntu, then it outputs the id. Very simple. Then we are mentioning the key pair, then monitoring is equal to true, then we are providing the subnet IDs and security group IDs. So we are giving both of them. Now public IP address is equal to true, as we need it because this will be the jump box, so we need a public IP address for this, and we are keeping it in the public subnet, as you can see here. Now we are giving some random tags over here. You can ignore it, but if you want to give, then you can definitely give it. So this is the Bastion host. Now let's move to EKS.tf, and this Terraform code creates a security group for the EKS cluster and complete Amazon Elastic Kubernetes Service Cluster using this Terraform module. So here also we are using modules. So first of all, we are creating a AWS security group. That this is the additional security group for the EKS cluster. I'll be explaining why we are creating this one, and below that we are creating the EKS cluster using the module. Again, it will pick the module from the official Terraform registry. Here we are providing the version, and the name of the cluster will be Terraform test Terraform cluster, and the version will be 1.33. You can do it 1.34 as well. So I'll be using 3.4, and here I'll be naming it Terraform cluster. All right. Then if you want to provide add-ons, then we are using core add-ons, then EKS pod identity agent, and kube proxy and BPCNI. So these are the required add-ons for our project. So I am adding these 4 add-ons. Endpoint public access, which is false, which we have set to false. As I told you, we are keeping it to only can be accessible within the VPC, so no one outsider can access our cluster. All right, so we are keeping our data nodes, which is our worker nodes, in the private subnet. Along with that, we are keeping our control plane endpoint public access is set to false. Then this is the optional, it add the current caller identity. So when you enable this, then if you, so what is your caller identity? So let's say you have done AWS configure. So when you do AWS configure, so that particular identity has to have that cluster access. So when you enable this, when you set it to true, then EKS gives that particular identity permission to administer the cluster. All right, then here we have mentioning VPC ID, then subnet ID, then additional security group ID, which is this fellow. Here if you see in the security groups, I have mentioned the Bastion host security group. When we will talk to Kubernetes API server, it talks via HTTPS. So from Bastion to the control plane, there should be access, and that access is done using HTTPS protocol. So for that reason, we are enabling 443, and we are attaching this security group to our cluster, and only the traffic from Bastion host is allowed. So we can only administer our cluster from the Bastion host. No one else can talk to the API server of the EKS. So this is a highly secured EKS cluster. So in every step we are ensuring the security is available. Then we are creating the node group, and we are giving the AMI type is Amazon 2023, Amazon Linux 2023, and instance type we are taking C7i Flex Large. If you are using the AWS account free tier, which gives you $100 credits, so this is a good instance which you can take and practice and implement this project. So minimum size I have kept it 2, maximum is 10, and desired is 2. If we require, then like further we can increase the size. That is not a big deal. And at last we are giving the tags. Fine. Now the last one which is pending is outputs.tf. So this is very self-explanatory, like it outputs whatever data Terraform computed, it outputs those data. So here we are just outputting the cluster name and the Bastion public IP. We need it because we have to SSH to that machine, so we need the Bastion public IP and the VPC ID which we are outputting. So this is all the Terraform files which we have currently. Now we'll do AWS configure. Let me just save this file, and we'll implement this Terraform. Like we will be running plan, we will be running apply to create all the infrastructure using Terraform. So now let's do AWS configure, because I need to authenticate with AWS to run Terraform. Then only Terraform will have that access to create the infras in AWS. So before configuring it, we need to create the access key and secret access key in AWS. So I'll just go to my AWS console and create a IAM user. Great, I have logged into my AWS console. So to get the security credential, you can just go over here in your root account. You will find the security credential option over here. So you can just quickly create the security credential from here. Otherwise what you can do is you will just create the user, and in that user you have to create the security keys. This is not a good practice to create your security credential in the root user. So the best practice is to create a user, and then inside that for that particular user you will create the security keys. So I'll be creating a user first. Just click on create user. I'll just name it Terraform AWS, and next. Here, as I need to create multiple resources or multiple services, I'll just give this user to administrator access, then click on next, and here just create the user. Nice, this user has been created. Now just click on that particular user and just go to the security credential tab, scroll down and search access key. Now here you can create the access key. Give like you just need to mention some use cases over here. So I'll just simply give command line interface and just give the confirmation and click on next, and then create access key. So here you can copy or just download the CSV file. Don't close this tab without copying or without downloading the CSV file, because once you close it you won't be access it. All right, so I'll be just copying this access key, and don't share this access key and secret access key with anyone, because once you share it, so the person you share will have the access to your AWS account. So I'll be just for this demonstration purpose I'll be using this access key and secret access key in front of you. But once this is done, once my project is done, I'll be deleting this particular user. Right, so I'll just copy this access key, and what I'll do is I'll do AWS configure, and here I'll be giving access key ID, and then copy the secret access key and paste it over here. Then the default region you can just provide US East 1. You just type US East 1. So this is already suggesting me, because I already had configured it in the past. When you are doing it for the very first time, so you will be giving this security key and access key, and then you have to type the region name and the default output format you can type it text, table and JSON both. So for me I kept it table. You can provide it JSON as well. So this is configured. How will ensure that your AWS configure is done successfully? So basically you can type AWS CLI commands, AWS STS get caller identity. This should return the username. As you can see, it returns the username, which is Terraform-AWS. So now our AWS configuration is done. The authentication part is done. Now we'll go to our VS Code. One more thing, like I used this bash terminal. You can also use VS Code's terminal as well, which will give you the same bash terminal. As we authenticated Terraform with AWS, now we'll run Terraform init. So here in the Terraform directory we have all the Terraform files. So we need to cd to Terraform and then do Terraform init. And what does Terraform init do? Basically it downloads all the provider you have mentioned and downloads all the modules, and then initialize in the current directory for Terraform. So once we will do Terraform init, then you will able to see it. See, it is initializing the backend, then initializing the modules. It is downloading the modules and downloading the providers, and inside the .terraform directory it has been downloaded. See, this is the provider plugins. It is downloading. We got some error and it says could not retrieve the list of available version for the provider ASIC of AWS. No available release match the given constraints. Alright, you can just go to Terraform registry, just browse the providers, go to AWS. So here you will get the provider version. So the current version is 6.38.0. So I'll be mentioning that. Let's go to my code, 6.38.0, which is the current version. I'll just simply save it and run the Terraform init again. So this provider version and the Terraform version both are different things. Terraform version is for Terraform core version, but provider version is for the provider AWS version. Now it is installing the HashiCorp AWS 6.3 8.0. Let's see, this time it should done successfully. It has been successfully initialized. Let's run Terraform plan. So now our plan is getting generated. So as you can see, there will be 71 resources will be added, which includes our VPC, EKS, and all the networking resources like subnet, NAT gateway, and other things. So now just go ahead and do Terraform apply. Give the confirmation by typing yes, and it will start creating the resources in your AWS cloud. So it will take 15 to 20 minutes to create the cluster. VPC and all will create, and it will take less time, but to create the cluster it takes 15 to 20 minutes. So I'll be coming back once it is done. Alright, now as you can see, the apply has been completed, and there are 71 resources which is already added, and in the outputs we can see the Bastion public IP, the cluster name, and the VPC ID. Let's verify it in the console, AWS console. So I'll just quickly go to EKS and let me open VPC as well. As you can see, we have the cluster named Terraform cluster, and in the VPC section we'll be seeing the same VPC whichever we have mentioned in the Terraform configuration file. And let's quickly open the EC2 as well, EC2 service, to verify whether we have the worker nodes and the Bastion host ready. See, we have test VPC 01 ready, and last thing is EC2. Let's go and verify that. So we are in a North Virginia region. Go to instances running. Yeah, as you can see, we have our Bastion host and 2 worker nodes for EKS cluster which are running. And now if you see over here, we have the Bastion public IP, and as I told you that we can only manage cluster through the Bastion host, as the cluster is in private subnet, and we have disabled the public access for that control plane. So we need to go inside the Bastion host and configure again AWS CLI, and we will import the kubeconfig inside the Bastion host so that we can manage our EKS cluster, right? So let's do SSH. And as I told you, when you will run Terraform apply, you will be seeing the private key for the Bastion host. So this is the private key file which got generated once you apply the Terraform apply, right? So now we'll do SSH -i to provide the key, and then the username is Ubuntu, and the public IP of the Bastion host. Awesome. So we have SSH into that Bastion host. Let's do a update, sudo apt update. I'll make it full screen as our Terraform part is done. So we'll be moving forward. Let's visit our GitHub repository. So in the GitHub repository readme file, I have clearly mentioned all the steps, so which you can follow. Yeah, so after that, this is optional. You can also set up the Terraform remote backend. So for that you need a bucket. So you will be creating the bucket through console or through AWS CLI, whichever way you prefer. You can just create it and use that bucket as a Terraform remote backend, so that your state file will be storing there. Currently we have it in local. If I show you over here, if you see the Terraform TF state is stored locally. So if you want to store it in S3, or if you want to access it in from a centralized location, then you can store it in S3. So as we have it already here, so we will be migrating this local state to the remote backend. So for that First thing first, we need to create a S3 bucket. So I'll exit from the Bastion host. I'll be showing this remote backend. Then we'll go again inside that Bastion host and we'll implement the things. Okay. So to create a bucket, I'll just copy the code from here and paste it here. So I'll change the bucket name. Let's say I'll add some random number 1 2 3. So the bucket name has to be unique. Now let's enable the versioning and the bucket encryption. I will do one by one. First enable the versioning. Make sure the bucket name is correct. -123. And again we'll enable the encryption. Again make sure the bucket name is correct. -123. Hit enter. Now let's add this backend block inside the terraform.tf. I'll copy this. We already have terraform.tf. Inside this you can just mention the backend block. Here I have mentioned the bucket name is this, the key will be S3 backend, and this is the bucket name. I'll make sure the bucket name is correct, and the region I have mentioned here. Alright, I'll just save this and I'll run Terraform init again, so that Terraform will take this bucket in account and it will initialize it again, so that the terraform.tf state file, it will migrate from local to the remote backend. I'll show you in the AWS console as well. So here in the S3 service, as you can see, I have a bucket called DevOps dog -terraform backend bucket 123. So this is the previous bucket which I had created a long back. This is the bucket which we have created now. If you go inside that, there will be nothing, right? Now we'll do Terraform init. It will initialize the backend. It will ask us to migrate the local tf file to the backend, new backend. As you can see over here, it is asking me, do you want to copy existing state to the new backend, and do you want it? So we'll type yes. Awesome. Let's go to our S3 bucket again. Now if I refresh it, so if I refresh it over here, as you can see, we have the state file called S3 backend. Alright, so this is done. Now we'll go inside that Bastion host and we'll further configure our EKS cluster, right? Go back to our repository and this part is done. Now we'll SSH. I'll just maximize it. I'll make sure you can see it properly. So I'll just increase the font size a bit. Great. I'm hitting up arrow just to get that SSH command which we had executed before. Great. Now we are in the Bastion host. I'll just clear the terminal. Now what I'll do is I'll install the AWS CLI in the Bastion host, then kubectl client, Helm and EKSCTL. All these things I'll be installing in the Bastion host, and all the installation resource documents I have provided here. So you can just click and directly jump to the right documentation. So here you can just choose Linux because we have the Linux machine, and I'll copy the curl commands and all just to install our AWS CLI. Okay, the zip file is downloaded. Now let's unzip it. Okay, the unzip is not installed, so first we'll install the unzip binary. And then install it. Alright, it has installed. Let's verify. AWS hyphen version. Great. Now let's install the next tool, which is kubectl client. Open the link in a new tab. Here are the commands to install the kubectl client. Yeah, this is the command. Curl on Linux. So we'll install using native package management. Just copy it and paste. Now let's update it again. And then install the kubectl. Then we'll verify the version of it. Yes. So this is done. Now let's move to the next tool, which is Helm. Again, I have provided the installation documentation over here. You just open it and install. Follow the steps to install it. Alright. Now it shows us through package managers, and we are using apt. We are using Ubuntu, and this is the installation steps for Ubuntu. I'll copy the whole command and I'll execute it over here. Let's verify. Helm version. Alright, we have Helm ready. Now what is the next one? The next one is EKS. Why we need EKS? Just to manage our cluster, we'll be using EKS, right? So let's open the documentation, and here for Unix, for Windows, for okay. So I'll copy the whole command once again. Go to your Bastion host and paste it. Just see EKS version. Yeah, we have all the tools ready. Now let's import the kubeconfig file. So we have kubectl, which is the client for the Kubernetes. Using this client, we can manage our kube API server, right? We can talk to our kube API server. So for that, we need the kubeconfig file. So to import that kubeconfig file, we have this particular command. We'll just copy and paste it over here, and we'll replace our region and the cluster name. So the region is US East 1, and the cluster name, what is the cluster name? I forgot. Let me check. The name is Terraform cluster. Just replace your cluster name. Now import. Okay, it says there are no credentials, so we have to do AWS configure first. Okay, so let's do AWS configure. Let's do one thing. We can use the same credential which we use to authenticate the Terraform, and I can use the same credentials over here. I'll not create a separate user for it. I'll just create a new terminal, and in this terminal, so this is my local machine, right? And here, if you go to this directory, you will find the credential. So I'll take the same credential. In your case, you can go to your local machine and find your credential from the directory I'm going to show over here, or if you downloaded the credential, then you can just copy paste the same. Okay, so I'll copy this credential from my local machine to the Bastion host. So there will be no context as it got failed, but let's verify kubectl config current context. Sorry, it context, not contexts. So the current context is not set, right? So let's import the kube config file again. Now it should work, right? So the context has been added. Let's verify the config current context. Yes, so it is pointing to our Terraform cluster. All right. Now let's do kubectl get nodes. It should list our nodes. All right. So the setup is done. The Kubernetes setup is done. All right. Now let's see what is the next step. Now we'll install the load balancer controller. So why we need AWS load balancer controller? Because we are using gateway API, and our controller will manage the gateway API and the load balancer both. So whenever we'll be adding one route, so it will talk to the AWS load balancer controller, and that load balancer controller will manage the load balancer, and from the load balancer itself the traffic will flow to that cluster, isn't it? So let's install the load balancer controller now. I already have provided the documentation which you can follow, but the same thing also I have added here. So you can either follow the official documentation, or you can follow this step in the readme file which I have mentioned it already here. Let's first ensure that we have the IMDC provider available in the cluster. You can skip this step because we already have the cluster, and we already have the IDC provider integrated with the cluster itself. So we'll create the IAM role using EKSCTL. We'll first download the policy document, then we'll create the policy, and then we'll add that service account which includes the role, and the role we'll be creating by using the policy. All right, then we'll install the load balancer controller. So as part of our Terraform apply, we already have the IDC provider. How we can ensure that? Just jump to your Bastion host and type AWS EKS, describe your cluster, describe cluster, then we'll give the cluster name which is Terraform cluster, and we'll query for IDC issuer. See, we already have the OIDC enabled in the cluster. So we'll now download the policy. I'll copy the curl command from the readme file, and here we have the policy document, right? Now we'll create the policy using this downloaded document. Okay, it says it already exists, but in your case, if you are doing it for the very first time, so it will get created successfully. I have already a policy named AWS load balancer controller IAM policy, so it is throwing me an error saying that entity already exists. We'll create the role using this policy. By using this EKSCTL command, you just need to replace few steps, the cluster name and the AWS account ID. Cluster name is Terraform cluster, and then the AWS account ID I'll replace. You can copy your account ID from here and paste it, and the region code also you have to mention. Now hit enter. So the role is getting created. When you use EKSCTL, so on the background it uses cloud formation template to create the resources in the AWS cloud. Let's wait for some time. Great, it has been created. Now we already installed Helm. We'll install our load balancer controller through Helm. So first we'll add that Helm chart repository in the readme file. You can just copy, then we'll update the local repository to make sure that we have using the recent charts, and then we'll install the controller by specifying this command. And here we need to replace few settings. For example, the cluster name, region is correct, the VPC ID you have to replace, and rest all are good, right? And as we are using the gateway API over here, So you need to add this controller config NLB gateway API is equal to true, and controller config feature gets ALB gateway API is equal to true. So if you are using ingress controller, then you don't need to set these, but as we are using gateway API, so you have to explicitly tell the controller that we are using gateway API. All right, now let's change the VPC ID. Let's go to console and copy the VPC ID from there. This is the VPC ID. Paste. Now let's hit enter. So the load balancer controller is installed. Let's verify. As we mentioned here, the namespace is kube system, so it installed in kube system namespace, and we'll verify by executing the command kubectl get deployment -n for namespace kube system, then the name is AWS load balancer controller. Let's verify it. As you can see, it's available and it's ready. Then let's move to the next step. So we'll go to the readme file and we'll see what is the next step. So the next step is to install the gateway API. Again, I have provided the official documentation over here. So if you want to follow the official doc and implement accordingly, you can just go ahead and do it. But the same thing I have mentioned it here. So it will be a bit easier for you to refer all the steps in the readme file as well. First, we need to install the CRDs. There are 3 CRDs. These are standard API CRD. Then we have experimental gateway API CRD, which is optional, but it is used for layer 4 routes. This is for layer 7, this is for layer 4 routes, but it is optional. You can either install it or you can ignore it. Then at last we will be installing load balancer controller gateway API specific CRDs. So there will be 3 CRDs we will be installing, whereas this is optional, but this and this you need to install it, right? So I'll copy and install one by one. Go to the next. Then at last we'll execute LBC specific CRDs. Great. Next is to create the manifest and apply them. So the first thing first is to create the gateway class and the ALB configuration and gateway. Okay, so I'll be explaining what does this gateway class do and what does this ALB config do and what is this gateway. I'll explaining the YAML manifest, but here you don't need to write this and create this manifest. You just need to clone the repository. In the specific directory you will be finding this manifest already available to you. So I'll clone the repository again inside our Bastion host. Now let's cd, and here you can see we have gateway API manifest directory. Just cd to that directory and you will find all the manifest available. So before I explain the gateway API, let me just explain you why exposing the application in Kubernetes is needed. So as you know, in Kubernetes, applications runs inside the pods. You already know that pods have the dynamic IP addresses, and this can be restart or scale, right? But external users cannot directly access the pod IPs because the pod IPs are for internal purpose, like cannot be resoluted from outside. So the user cannot access the pod directly. So that's why we need to expose our application to the outsider world. So Kubernetes provides multiple methods to expose the application, such as cluster IP, node port, load balancer, ingress, and gateway API, which is the newer one. The gateway API is the newer one, right? And each one solves a limitation of the previous one. Let's say node port is the a better version of the cluster IP, and load balancer is the better version of the node port, and ingress is the better version of the load balancer, and now gateway API is a little bit better version of the ingress. So each one solves the limitation of the previous one. So what does cluster IP do? Cluster IP exposes the application only inside the cluster. So first we will have the pod, and the pod will go to the service, and from the service it will reach to the another pod. That's how it works. So when to use the cluster IP? Let's say you want internal microservices communication, you want to call your backend service, you want to call the database which is inside your cluster. So there is a limitation for cluster IP. It is not accessible from outside the cluster, and that's where node port comes into the picture. A node port service exposes the application on a port of every node. For example, here if I do kubectl get nodes, we have these two nodes available here. If we expose a application using node port, that application we can access using every node's IP address. So from the internet, you just need to mention the public IP of this node, or private IP will accessible within the network, and using that port whichever you have exposed using node port, you can access that application using the cluster node and the port. Similarly, load balancer service automatically creates a cloud load balancer. We are using EKS, so if you use a cloud provider like Azure and GCP, when you will add a service type to load balancer, so it creates a cloud load balancer. EKS, it creates a elastic load balancer or an application load balancer. So you will get a managed cloud load balancer. Then there is something called ingress routing. So to solve the limitation of the load balancer, Kubernetes introduced a Kubernetes ingress, and it allows multiple services to share one load balance. Let's say you have multiple services, like you have microservices, and that microservices application has multiple services. Let's say UI, then backend, then database, then other microservices like booking, then your cart. So these many microservices are available. Let's say we are running one company, and in that company you have multiple projects, and you want to access with one domain, but there will be different host names. Let's say Amazon has prime.amazon.com, then it has aws.amazon.com. So like that scenario, in that scenario you will be using ingress, and the ingress needs a controller. In market you will be finding nginx ingress controller, then HAProxy ingress controller, AWS load balancer controller, that is also an ingress controller, traffic ingress controller. So these are the different types of ingress controller. I'll not go in depth, I'm giving you a high overview how these things works. Then there is some limitation of ingress, like only HTTP or HTTPS are supported. It's a load balancer, layer 7 load balancer, so you will be finding that ingress only supports HTTP and HTTPS, and different controllers, like I said, multiple ingress controller available in the market, so different controllers behave differently. Then there will be limited routing capabilities, it is very hard to extend. So, and there is no clear role separation, so whoever gets the access to that ingress controller, they can manage the load balancer. So there is no clear role separation. So because of these issues, Kubernetes introduced Gateway API. So the Gateway API is the next generation replacement for ingress. It provides you more flexible traffic routing, better role separation, and support for multiple protocols. Let's say gRPC, then your HTTP and HTTPS. It supports you multiple protocols. And in the Gateway API, we have different components, and this is what we are doing now. If I do ls, so you can see we have gateway class, gateway, and one lb config over here. So there is another thing called route, which you will see, I'll explain you that as well. So these are the main things. So lb config, this is not the component of gateway API, but here in AWS, as we are managing our load balancer using gateway, so for AWS only we are using this alb config.yaml. It is specific to AWS, but in general, if you implement gateway API, you will be needing three things. One is gateway class, one is gateway, and another one is route. So as we are doing EKS and we are implementing gateway API, so this alb config is required. Great. Let's first see gateway class. What does this do? We already installed the CRDs. As you can see, the kind is gateway class, and the controller name we have mentioned gateway.k8s.aws/alb. So this is the load balancer controller. That's what we are mentioning over here. I already provided you the documentation. You can go and check the documentation and you can read more about it. This is very simple. Now let's view the gateway. So here the kind is gateway, and we are giving the metadata, which like we are deploying it in the default namespace, and the name will be app ALB gateway, and here we are providing the gateway class name which we have created here, right? So the gateway class name is here and we are providing the gateway class name, and in the parameters reference we are also providing the load balancer config, which we will see after this. Then in the listener, so in the load balancer you have listeners, right? So we are providing HTTP listener and HTTPS listener, and we are allowing routes from all the namespaces. So this is the beauty of load balancer. If you want to allow route from a specific namespace, and that's also you can mention it in the gateway. So here I'm allowing the route from all the namespaces. So, and I'm adding both the listeners HTTP and HTTPS. Then let's go and see the ALB config. Similarly, we have the kind as load balancer configuration, then the metadata we are giving it, and as I said, we will be implementing the SSL and TLS. For that, we will be needing a certificate, and here for certificate, I am using AWS SCM. If I go to my AWS console and I will go to the SCM service, which is certificate manager. If I list the certificate, then here is the certificate I have. If you don't know how to create a certificate, then I already have created a video in my YouTube channel. I'll even add that video link in the description. You can just go and check it out, or I'll add that video link in the I button. Just check that out. So here I have the certificate all which is ready. Just copy the ARN and paste it over here. Great. I have added the same ARN over here, but in your case you have to add your own ARN. So the default certificate is this. So in the load balancer configuration, I have mentioned the protocol port, and we have added the certificate, and the name is app gateway lb config. Great. Now let's implement this. I'll apply one by one. kubectl apply gateway class, then gateway, and then the load balancer config. Okay, I got some error. It says line 13 couldn't find expected colon. Okay, let's view line 13. Okay, here is the mistake. I forgot the space. Yes, now it should work. Cool, it is created. And I forgot you to explain the routes. So the in gateway API there is a component called route, and it defines traffic routing rule, and those includes like HTTP route, TCP route, UDP route, or gRPC route. It can be anything, whichever you want you can implement that. So this file configures the AWS ALB settings used by the gateway API. Alright, we'll be seeing route. When we'll implement that, we'll be seeing what a route does and how it is exactly. We'll be seeing that while we'll be doing the route. So now we have everything created in gateway API. Let's verify kubectl get pods. Sorry, not pods, kubectl get gateway class. We have the gateway class which is accepted is equal to true. Just make sure that this part is true. Now let's see the gateway. So you can see it successfully created a load balancer. Let's verify it in the UI. See, and get created. Now let's see the load balancer configuration. We have everything ready. Great. Now in the next step we'll be installing the external DNS. And what does this external DNS do? So whenever there is a request to add some host name in the cluster, so it automatically should update that in the Route 53 or preferred DNS zone. So here we will be using Route 53. So we want whenever there is a request to add some DNS records, the external DNS should go to Route 53 and add the DNS records. So we'll be not doing any manual DNS record updates. So this should be completely automated. That's why we are using external DNS. So let's go and deploy the external DNS now. So first thing first, we'll be creating an IAM policy, because in that policy you have to give certain permission to external DNS so that it can go to Route 53 and list the resource record set. Then it can list the tags for resources, and it can change the resource record sets, and the resource permission we have to give, let's say hosted zone. So there are certain permission which we have to give to external DNS so that it can perform the action on Route 53. All right, so we'll be creating this policy.json, and after that we'll be creating a policy out of this document, and then create a namespace, and we'll create a role using that policy, and we'll be using pod identity agent to deploy external DNS, right? So there are too many ways you can deploy your workloads in AWS EKS. One is IRSA, which is I am role for service account, and another one is pod identity agent. So IRSA is the older method, whereas the pod identity agent is the newer method. So we'll be seeing both, as I told you initially, but in IRSA you have to explicitly add that role or inject that role in the pod, but for identity agent you don't need to add that roles, because identity agent, it will talk to OIDC provider and talk to the resources whichever you granted. All right, so yeah, let's do it. Let's deploy external DNS. So this policy.json, you will find it in the appropriate directory. If I do ls, then here you will find, here is the directory, just cd to external DNS and do ls. So here you have already policy.json present. So let's create policy using this particular JSON document. So I already have it in my console or in my AWS account. So it says entity already exists, but in your case, if you are doing it for the very first time, it should get created. Let's add some env variable. So I'll list the policy, and the policy name is allow external DNS update, which is this fellow. I'm adding that into a variable, and the cluster name is Terraform dash cluster. Great. And we already have the add-on for pod identity agent in our cluster, so you don't need to create it. Let's verify whether we have the add-on ready or not. Let's go to our EKS cluster, click on the add-ons. We should have the pod identity present. Yes, so we have EKS pod identity agent present. Let's create a namespace called external DNS, and inside that we'll be deploying the external DNS, right? So kubectl create ns external dash DNS. Now let's create the pod identity association. We need to associate that, so we have to create the pod identity association. And here as we already set that env variables, which is cluster name and the policy ARN, so we are adding that here, namespace external DNS, service account name is external DNS, and the role name is external DNS pod identity role. Great. So this will be the role name, and the policy we are attaching this one, right? Let's hit enter. So unlike the IRSA method, pod identity requires no another steps like service account annotation and all. So since the pod identity association will bind the service account to that given IAM role, hence the policy holding the request set of permission, and the EKS pod identity agent handles credential injection at runtime, right? So I got some error. I think, yeah, I already have this role name available in my IAM, so only it's failing. Let's go and verify that. Yeah, I already have it ready. So 13 days back I had created it, so it's already available, so it was failing. Okay, no problem. In your case, it should go through, like it should create a role named this, right? Great. Let's move forward now. Yeah, all the prerequisites are done for external DNS. Let's add the Helm repository of external DNS, and let's deploy it. So first thing first, I'll add the repository, Helm repo add external DNS. Then this is the link of the repository, and it has been added to the repositories. Now deploy it in our namespace. So Helm install external DNS, then the path is this. the repository path is this, then the namespace we have mentioned external DNS which we had created earlier, then this is the version. Great, it's deployed. Now let's verify. So it's not ready yet, let's wait for some time. Yeah, it is ready. You can see it is ready, right? We are integrating with gateway API, right? So we need to ensure that whenever there is some request to update the records in a particular DNS zone, so it should take that update and it should write or remove from the DNS zone, right? So to make that work, we need to add something extra in the values file. And how would you get that values file? Here, to get the values file, you can just type helm show values external DNS, then the version name you have provided. To fetch that value and redirect it to a file called external DNS values 1.20.0 YAML. And when you get that values file, you can edit that values file. You can just go to the sources section and you can just make sure that in that sources you will have service, ingress, gateway, HTTP route, TLS route, TCP route, and UDP route. Why we are adding this? We are ensuring that whenever there is a request to add some records or remove some records from the services, ingress, or HTTP route, it should pick those requests and update the DNS records. So only we are adding services, ingress, gateway, HTTP route to this values file. So you'll already having service and ingress, but as we are using gateway API over here, so you need to add this as well. All right, so I already have this values file ready in that external DNS directory. You can just find it here, or you can just fetch it using the helm command, right? So if I show you this external DNS values and I'll try to find the sources. See, so in the sources I already have service, ingress, and then gateway HTTP route, gateway TLS route, TCP route, UDP route, right? So I already have this. So I'm gonna update my external DNS deployment. You can use helm upgrade command, helm upgrade external DNS, then this is the path, then -f for file. So this is the values file. So when you give -f for file, so it will take that file as a values file, right? And I'm giving the namespace and version, right? Hit enter. Now this deployment has upgraded. Let's verify if the pods are running. Great, it is running now. So the external DNS part is done. Let's move to the next one. Now we will deploy ArgoCD. So we'll be installing ArgoCD through Helm, and we'll do some modification in the values file, and after that we'll install the chat, and we'll be adding the target group configuration, and we'll make sure that this is exposed through the gateway API. All right, so let's go and start it. I'm gonna copy this, adding the repository, and then I'll just change the directory to ArgoCD to ls. So I have already the values file available here, but as I told you in the previous external DNS section, you can fetch the values file and redirect it to a file, and you can later on you can modify that, right? So I have already given you the command as well. So this is the command to fetch the values file and redirect to a file, right? So let me open this file in VI editor, ArgoCD values. So now here we'll do 2 to 3 things. First, just find the param section. So this is the param section, and here you have to make sure server.insecure is set to true. Why we are insecuring it? Because we want the TLS to be terminated at the ingress level, not in ingress level, like load balancer level. So we don't want ArgoCD run in the secure mode, because we are securing it in the back step, I mean in the load balancer step. So that TLS of loading happens in that load balancer step. So that's why we are making sure that it runs in insecure mode, right? Next is just go to the config section. So in the config section, CM, you just make sure that the create option is set to true, and this customize.build option is set to dash dash enable dash helm, right? Why we are adding this particular line? Because customize require it to combine helm values and the manifest file, as I explained in the beginning. So we'll be using customize as well while we'll deploy our application. So in our application there will be some point we'll be using manifest, and we are using helm as well. So we want whatever we give as a helm and whatever we give as a manifest, so those should combine and deploy the application. So to combine them, to combine the helm chart and the manifest part, we'll be using this customize.build option is set to enable helm. So our application is deployed as a helm chart, but later on if we need HTTP route or some other dependencies, we will be doing, instead of modifying the helm chart, we will be adding those as a Kubernetes manifest. So we need to combine both of them, like the helm chart and the Kubernetes manifest. So only we are adding this file, this line. Then we have to expose our ArgoCD so that we can access the UI and deploy the application or view what is the current status of our application. So to expose our ArgoCD UI, as we are using gateway API over here, so we need HTTP route, right? So I'll just search HTTP route. Yeah, so here you just make sure this is enabled, and just scroll down a bit. So in the parent reference, you just make sure which gateway it is referring to, and the namespace of the gateway and the section name. So there will be multiple section, right? HTTP and HTTPS. So we are making sure the section name is HTTPS, and then we have the host name, like what will be the host name to expose this application. So this is the host name we are mentioning. Then the rules, that's all we need to expose our application, right? Now we had added the repository, but we didn't install it. Now let's install it. So helm install ArgoCD, then we are making sure we'll refer this particular values file, then this is the version, then at last we are mentioning dash dash create namespace, so that it automatically create a namespace called ArgoCD, and it takes the values file and deploy the application, right? So before that I want to show you few things. Let me just go to Route 53 in the hosted zone. So this is the domain I have available in our hosted zone. You see there are no records called argocd.devopsdoc.site, but as we deployed external DNS in our cluster, so when I'll apply this, and I already have mentioned in the ArgoCD values file, we need a host called argocd.devopsdoc.site. So now as I apply this, then the external DNS comes to the action, and it should create a record in our Route 53 hosted zone, right? So let me just hit enter and install the ArgoCD. Great, it has been installed. So now we have to make sure that we will set the target group config for the ArgoCD. So why we need that? Let me just explain you. Let me go to the load balancer section. So you can see we already had implemented it, but there is no listener and there is no rules. Why? Because when you will use LBC controller, so as a part of gateway API, we explicitly need a target group configuration. Then only this listener and the rules will be added, right? So we'll be adding a target group config YAML. So in that we'll mention the typical settings like health check path, health check interval, what will be the target type, like other settings which you do for the target group config that controls the load balancer target group behavior. And target group is where your load balancer sends traffic, right? But when we will implement another gateway APIs like K gateway, Istio, Kong, or Ingress Nginx gateway, so in those these setup are not required. As we are implementing LBC, you need this target group configuration additionally, right? So if you do ls, here only we have this target group config.yaml. If I show you target group config, so here you can see this is the name of the target group config and the target reference, which is ArgoCD server. So this is the service we are providing over here, and the default configuration target type is IP. This is what, so I'm just gonna apply it. Let me just check the service kubectl get svc hyphen ArgoCD. You see here, so this is the ArgoCD server and we are exposing this. So in the target reference I have added ArgoCD server. Alright, now just apply kubectl apply hyphen f target. Verify that kubectl get target group configuration in ArgoCD namespace. Alright, we have it. Now let's go to the UI and let's verify it. Just refresh that. As you see, now we have the listeners and rules, and we have two rules over here. And if I show you in the hosted zone, the external DNS should have added that records in our hosted zone, isn't it? So just refresh that page. Okay, I think there are some issues. We have the certificate over here. Let me check the rules first. So in the rules we have it. I know we can't access it. I need to see. Yeah, something happened in the external DNS section, so we are not having the recorded set. Yeah, let's go and debug that. kubectl get pod -n external DNS. Yeah, it is running. Let's see the pod logs. So as you can see, we got some error, and here it says no EC2 IMDS role found. So I think the role which we had attached with the pod identity agent, the pod did not get that role, so only the external DNS has no access to a route 53. So let's do one thing. Let me go to the UI and IAM section, and let me delete that role and create it again. Okay, so this was the role, external DNS pod identity role. I'll just delete it and we'll try to create it again. Now let's go to the section again, external DNS. Yeah, here it is. I'll just copy this and try to do it again. So it says the stack is already available as we ran it in the previous step. So it is already available, but it is in the failed state, I know. So you have to delete that all the stack first. To do that, you can do it manually in the UI, or you can use the CLI command. Let me go to the cloud formation, and the stack name is this. This is the stack name. I'll just copy. This is in fail. Failed state. So I'll just delete this stack. Deactivated save. But in your case, it should work because I had it, so I didn't create it again. So it got failed. But in your case, if you followed the external DNS setup step by step, it should work. But in my case, it was already available, so I did not create it. But later on, it gave me that error. So I did not delete. Yeah. So now we'll go and execute the same command again. So after that, we'll just try to upgrade it, right? Great. It failed again. So describe the stack events. So it's saying the role create got failed because I had created the same role in another stack. So in this stack, this role is already exists, it's saying, and it's failing to create one. So let me just go to the stack section again, and in the stack section, let me see if I had it earlier. Yeah, if you see, I had created a long back. So what I'll do is I'll just delete this stack again. I'll delete the older and the newer one, and I'll create it once again. This is the older one, and that is the reason it was failing, and I'll delete this as well. And I did not get any error because you see this is the I executed with test Terraform cluster, and this one has the name of Terraform cluster, so I did not get any error. So I'll delete this stack as well. Now it should work, but you are doing it for the very first time, so when you install external DNS, this should work for you, right? Great. Now let's go ahead and create this pod identity association again successfully. Great, it got succeeded now, right? And we'll upgrade, or let's see the logs. If the log says all fine, then we don't need to upgrade the external DNS. Okay, let me just upgrade that. This is the upgrade command. Yes, now let's do kubectl get pods -n external DNS. So there is a typo here. There is no change. Okay, I'll do one thing. I'll deploy it again. Helm uninstall external DNS. Yeah, this is uninstalled. Now just install it again. Check the ports. Let me check the logs again. Great. You can see it says records were successfully updated in the zone name called DevOps.site. If you go to the Route 53 now and refresh it, see, now we have ArgoCD.DevOps.site and other required DNS records got updated. And now if I take this and hit it in the browser, see, now we have the ArgoCD ready. Great. So now we need to give the username and password. To get the username and password, there is a default username and password available. Default username is admin, and the default password you can get it from the ArgoCD secret. Yeah, so this is the default secret which is auto generated by ArgoCD. I'll just copy this, and here I'll just type admin as a default username, and the password, paste the password and sign in. So once you signed in, the first thing you need to do, which is to change the password. Go to the user info section, and here update the password, the current password, paste the current password, and type a new password. So I'll type a random password. Now confirm it, update the password, and you are done. So ArgoCD deployment is done. I know there were some troubleshooting in the external DNS. So basically it was my mistake. I earlier created one stack and I forgot to delete it, and for that reason we got that errors. So but if you are doing it for the very first time, so if you have done the earlier steps correctly, like how I did the deployment for external DNS, then you won't be getting this many issues. But yeah, this is a good thing that you already saw the troubleshooting. Further, if you get such errors, so you can troubleshoot it in a better way, right? So the next step is the CI part. So we'll be seeing in the GitHub action. So I did some modification, so I already mentioned it here. So initially when I forked that repository, it was completely kind of a single monolithic repository. So I converted that. I make sure individual images exist for individual microservices to improve the modularity and make sure it run as an efficient CI/CD workflow. So I pulled it. I pulled the official Docker images, and I make sure every microservices is having separate container images, and I stored them in GitHub container registry. And accordingly, I have updated the templates, the Helm templates, so that it can reference to those images, because now the images address got changed. I have updated the Helm template so that it can point out to the newer images which I stored in the GitHub container registry. So once you have the images in GitHub packages, connect them to the repository so that it shows up and link to the repo like this below. Duplicate it, I can show you. So as you can see, all the packages are available to this repository. I have linked it. If I go to my profile, so in that profile, in the package section, I have this ready and I have linked it to the repository. And if you want to see how to push the images to GitHub container registry, the same thing. At the last, you can just go and verify it, how you can pull the images, and how to push, how to update that, and how to push your newer image in the GitHub container registry. So basically, you need to create a personal access token and then give the permission as read and write, log into your container registry and tag it and then push it. So this is how I got my images in GitHub container registry, as you can see it here. And then you have to connect it to the repository. That's all. And you will make sure this is public. As you can see, it is linked here. So how you can link it? Let me show you how to link it. In the packages, let's say I want to link it to the repository. Go to the package setting, and in the package setting, you just add the repository and give the role as admin or write role. Write role also works. When you add the repository, you will find all the repository listed in your GitHub profile. Then you can just select and add. That's all. And if you want to make this public, you just change the visibility over here. As you see, all the packages are in public now. Similarly, if you want your Helm package to be updated in GitHub container registry, similarly you just create a personal access token, then give the permission, and then you can push it to the container registry. I'll show you that as well. So this is the Helm package we have. This is the Helm package we have for online boutique. So Helm package means our application, our e-commerce application. So I have packaged it and I'll deploy it as a Helm chart. So as I told you, now I have different microservices, like different images. So previously when I cloned it from the official repository, when I forked it, so it was kind of a monolithic application. So I made sure that I'll have multiple images for each of the microservices, and accordingly I need to upgrade the Helm chart. So I have updated the Helm chart and I push that Helm chart to my container registry. Once you connect your packages to the repository, it shows up something like this. Even I mentioned here, go to image, then package setting, then give the permission to that repo to run the action. Great. It's already shown here in the readme file. Now we'll break down the CI/YAML. Let's create our action file. Like we'll be creating one directory called .github/workflows. So inside the workflows, we'll be adding our pipeline, CI pipeline over here. So now before moving to the pipeline file, let me explain you the previous one, like the previous repository from where I forked, and the current one which I have now. And let me tell you what did I change and why I have changed that. Then we can move to the CI pipeline, right? So basically this is the repository from where I forked this project. So basically this is the source code which I forked, and I improved a bit, and then I'm deploying it. So basically if you go to the app Helm chart, and in the chart if you see, so in the values if you see, so this value has only one repository and without any tag. So this is the values file, right? And if you see in my repository, I'll go to the values file, and if you see here, you can see one important change I made. Instead of using a single common image repository, I have defined separate images for each of the microservices. You see over here, add service, card service, checkout service, right? And each of them are having different tags. And why did I do this? Because in a microservice architecture, and if you go to this original repositories, if you go to that original repositories template, so inside add service, if you go over here and if you see the images, so basically these images, so in the image section, if you see over here, it is referring to values.image repository. That means it is referring to values file. Let me just duplicate it so that I can explain it in a better way. Yes, so if you see here, so it is referring to values images repository. So this is the values file images repository, and after that it is taking values add service name. So this is the values. Then if you go to add service and name, this is the name, and then it is having values image tag or default chat app version. So if you are providing values, then it will take the values, otherwise it will take the chat app version. So here if you see, the chat app version is this. So that means if I want to change only one microservice, every microservice will get triggered and the CI pipeline will run on every microservice. So I have changed that here. Even I have changed the template. If you go to add service, now this is my repository. In the add service, in the image section, if you see over here, I am taking values images add service repository, then values images add service tag. So each of the individual microservices have their own repository and their own tag, so they are independent now. And why did I do this? Because in a microservice architecture, every service is independent. So each service should have its own image, its own version, and its own deployment lifecycle. For example, this add service has its own image, and card service has its own image, front end has its own image. Everything is separated. Now the first benefit of this independent deployment, let's say I make a change only in card service and I don't want to rebuild and redeploy all the services. I just update the card service image, push it and deploy only that service, and this saves my time and reduce the risk. And this fits perfectly with CI/CD pipelines. So in my setup, this is my repository. So in my setup, each microservice is built separately using the pipeline. It will build separately. So if you see, every service has different references. If you see, this is referencing to card service repository. Checkout service is referencing to checkout service repository, right? So each microservices is built separately using the pipeline, and each one produces its own Docker image. So this values.yaml, so this particular values.yaml which I have currently, directly connects to the CI/CD workflow, and it helps the version control and rollbacks become very easy. You can see I am using specific tags like 0.10.4. Currently I'm tagging all the application with the same tag. If I have different tags, then I can definitely update them, right? So if something breaks in one service, I can simply roll back only that service without touching others. But previously the default one, it is referencing to one service, I mean one repository. So if you update the source code, every service will get every microservice will get updated, which is not a best practice. And this is exactly how real production system work. Different teams manage different services, they release at different times, and they scale independently. So having separate images is not just a preference, it's a best practice. If we don't do this and instead use a single shared image, everything becomes tightly coupled. Even a small change would require redeploying everything, which is not scalable, right? So by separating images per service, I get better flexibility, better control, and a production ready architecture. And how did I do this? So basically I pulled the images, I took this repository, I just copied it, I went to my terminal. So from here I first pull that image, docker pull, and then the name is, let's say, add service. In the tag, the default one was using the default chat app version. So if I go to chat.yaml, So here this is the default version, and then I gave the tag over here so that it can pull it. So I pulled each and individual images and retag it and pushed to my GitHub container registry. Let me, okay, it got pulled, like it successfully pulled. Let me see by typing docker images command. So if you see, I have that images over here and I retagged it. So you can just simply do docker tag, then you can simply mention this, the old image with obviously with the tag, and after that I had my GitHub container registry over there, and I mentioned by using ghcr.io. Then the owner name, my GitHub account username is this, and then let's say I want to save it as add service, then I can simply specify add service and I can give a tag. So like this I tagged that image which I pulled and I pushed it to the GitHub container registry. So as I already told you how I pushed that image to GitHub container registry, I already have mentioned the same in the readme file. Here if you see, if you go to the end, so here only I mentioned how did I push the images to the GitHub container registry. So I gave the permission, then I did login. After login I did tag, as I showed you here only. I retagged that image which I pulled and I pushed it. So now it is visible in my GitHub account in the packages section right here. Similarly, I changed the Helm templates and I repackaged it and pushed it to the GitHub container registry. And the same thing, even I mentioned over here. If you again go to the readme file and till the end section, here I already mentioned how to create the Helm package and store it. So this is basically the same thing, but the command is slightly changed when push the package to container registry. So basically when you install, you have to use this OCI. So now let me explain you the pipeline files. So first I'll explain the CI trigger one. What does this do? So basically this workflow is the main CI trigger that detects which microservices got changed and then calls the reusable CI pipeline, which is the next one. So we are having two pipeline files, right? So one is CI trigger and one is microservices CI. So this particular file, this detect the changed service and build and push only those services. Let me go snippet by snippet. So in the first snippet, if you see on push branches main and paths, I am mentioning SRC, right? So what does this do? So basically when the code is pushed to the main branch, so on push means if the code is pushed to the main branch and if the changes happen inside SRC directory, in SRC directory we have all our microservices available. If you go here in the SRC directory, we have all our microservices available here. So these are the source code for each of the microservices. In add service, we have the application code for add service microservices. For cat, it has a cat service application code. So if the changes happen inside SRC folder, then only the pipeline should get triggered and runs. Then we have the permission section. So here I am giving the read repo permission and the packages write permission. So basically it will push the images to the GitHub container registry. So these are the permission I gave for. Then we have jobs. So the job name is detect changes. So basically it will detect the changes and it will find which microservices were modified. So here we are providing in which OS it should run and we are outputting the services. So the steps is check out the repository and then detect the change service, and then here is the key logic, like it will differentiate the changes between old commit and the new commit, and it will make sure it will only detect within the SRC folder. Then it will extract the service name and then it will do some kind of sorting, like it will remove the duplicates and it will output the service name. let's say front end, back end, and other services. So in the output services, we already mentioned over here, it will output the service name. In the job 2, if you see, it needs the detect changes. That means it is dependent on the previous job, and it says if needs detect change output service is not equal to this, then only it will run. That means it will skip if no service changed. That means if there is no changes in job 1, then it will skip, right? So that's what it do. And in the matrix strategy, if you see, I have provided the matrix strategy. Means like whatever service got changed, it will append here, and all the jobs should run parallelly. Then the important one will call the reusable workflow. So it will next, once these all steps are done, it will call the reusable workflow, which is our microservice CI YAML, which is this one. And all the service, it will pass the input to this with service. Let's go to microservices CI YAML. Let's understand what does this microservice CI do. So basically, this is a reusable GitHub action workflow, for building and scanning and pushing the Docker images for a microservice. So basically, it will build, scan, and push to the push the Docker image for a specific microservices. So the same thing in the first snippet, if you see on workflow call, that means this workflow is only triggered by another workflow. So it won't trigger directly. So whenever there are some changes, this file will triggered by another workflow, which is our CI trigger, right? And we are giving input service. So here only we gave the input with service, and here we give all the services which have the changes. We are passing the inputs to this file. This particular file we are passing the inputs, right? Required true and type is set to string. Then here we have the jobs. So the job definition, basically it is running on Ubuntu latest, and we are setting some environment variables. That means we are telling create a Docker image. The name should be GHCR, then the repository owner, then we are providing the name, and we are tagging that image by commit SHA, so that it is unique per build. Then let's break down the steps as well. So it will first check out the code. So it basically downloads the repo to the runner, which is Ubuntu latest. This is the runner we have. So it downloads the code, then it set up the buildx enables advanced Docker builds like caching, multi-platform builds. So it is setting that up. Then it is logging to GitHub container registry using the username GitHub actor and the token. Already we have gave the permission. Then it will build the Docker image, and it will build the image from this input service, whatever input is given by CI trigger YAML file. So this YAML file, whatever input it gives, it pass to the same, right? Then after that, and obviously it tags the image with the commit SHA. Then after that, we are doing a security scan before pushing the image, and we are using Trivy here to scan the image, and it checks for OS vulnerabilities. If you see, it checks for OS vulnerabilities and library vulnerabilities. And here if you notice, the exit code is set to 1. That means this pipeline should not fail even if the vulnerabilities is found. If you want in the scanning, if there is some vulnerabilities, then the pipeline should stop immediately. Then you can mention 1 over here. But as I am showing you the demo, so I am like intentionally keeping it to 0, because I don't want my pipeline to stop over here, and it will only show the vulnerabilities which has the label high and critical. And then we are pushing the images using docker push command. So it will push to our GitHub container registry. So the full flow will be, it will call the workflow, check out the code, build the Docker image, scan with Trivy, and push to GitHub container registry. And this pipeline will get triggered by this. So if there is any changes, this will get triggered. This workflow will get triggered. It will find the difference, and it will run a matrix. So this matrix will pass to this file, this workflow. So in this workflow, it will check out, build, scan, and push to GitHub container registry. So this is how our continuous integration happens, right? So in GitHub action, as you already know, like you have to create .github, and inside that you have to create a directory called workflows, and inside that workflow directory you have to mention your pipeline files, and GitHub action take all those pipeline files from this directory, right? The name could be anything, any name you can give here. but you should respect the directory structures, right? All right, so I already have this available in the GitHub registry. So let me go and change something in the SRC folder, and let's see if the pipeline is getting triggered. So I am here only in the SRC directory. Let me change something in the add service. So in the add service, let me change this file genproto.sh, and let me just remove this line, this comment line. Let me just remove this and commit the changes. So I'm committing now. The moment I'll commit, the pipeline should get triggered because I am changing in the SRC directory. So now only add service should get triggered, and only the images for add service should get updated. Now let's go to action, and if you see, this pipeline got triggered. Remove unnecessary comment in genproto.sh. If I go inside that, you see already it is in running state. Let's see it how it is running step by step. So it already checked out the code. Now it is building the images. Now it is running a tree scan. So before pushing only, we are scanning that image for the vulnerabilities. As you can see, we got some vulnerabilities, and this is high and critical, right? But still our pipeline is not stopping. It will still go through because in the exit code we set it to 0. And now let's change some another service and let's see if it is working. Let me change the front end, and I'll change this handlers go, and I'll just add this line and commit the changes. Now let's go to the action. See, it got triggered now. Let's see the builds. It was able to log into GSCR. Now it is building the image. It started scanning that image, and now it is pushing that image to GitHub container registry. As you can see, it's also reported some vulnerabilities which are critical and high, but yeah, as we mentioned, exit code set to 0, so it should go through. Great, it already pushed that images and the build got success. Let me go to the packages and verify. You see here, it published 1 minute ago, and it uses commit SHA for the image tag. It works for all the services. As I can see here, see, it is happening for all the images. You can see all the images have this many downloads, right? So this is how you will do the CI. Now we'll move to the CD part, and we'll see how we can integrate the CI and the CD. Great. Now let's move to the CD part. So as we already have the ArgoCD ready, which we deployed in the previous step, so we already exposed it, and this is the interface we have. Our application code, Helm chart, and all the Helm values are already available in the repo. Additionally, to expose our application via gateway API, we need HTTP route and target group configuration. So both these files we need, and which you can keep in the separate directory in the root repository. So in our case, I kept it inside this directory. I'll just duplicate and I'll show you. If you go inside microservices extract kube manifests, so here I have kept the HTTP route and target group. So why we need HTTP route and why we need target group, I already explained that while I was explaining the gateway API, so I'll explain it again. So basically the target group configuration is needed so the AWS load balancer controller knows how to forward the traffic from AWS load balancer to our Kubernetes pods correctly, right? So similarly, while exposing the ArgoCD, we configure the target group configuration and the HTTP route, right? So the target group is the bridge between AWS and our EKS cluster. So here we are explaining whether to send the traffic node or pod. Here the target type is IP, that means it will send to that particular IP, which is the pod IP. And the health check also you can configure over here. We have mentioned the target reference, so it will send to the front end pods, and the default configuration target type is IP. And what does this HTTP route do? So basically this is the traffic rules for the HTTP requests. It defines how the HTTP traffic is routed to our services. So the gateway is basically the entry point, like one gateway is equal to one load balancer. So if you deploy multiple gateways, then there will be multiple load balancers. But in our case, we want one load balancer, and within one load balancer the traffic should be ingressed, right? So that's why there is one gateway, and in the parent reference we have mentioned the gateway which we have deployed in the initial steps, and the section name is HTTP that I have mentioned. Both like HTTP and HTTPS, both I have mentioned over here, and the backend reference is front end, and the host name I have mentioned here is app.devops.site. So whenever I'll apply this HTTP route and target group configuration, so there will be one request for DNS records, and after that external DNS will perform the DNS records in route 53, and we can directly access our application in the browser, right? So this should happen when I'll apply HTTP route and target group. Rest all the gateway API components I have already explained you. So here I have added both the configuration, so you just clone the repository and apply that, or you can just write that. So one more thing, like you might be thinking why so our application we already did the packaging in Helm, right? So we already have the Helm package which is available in the GitHub content registry. So basically this is exposing our application, our microservices application. So why I kept separate? The reason is I want different controls for the application and for the network components. So our Helm template, it remains reusable. We can publish it later. Our Helm template doesn't affect to our network components such as HTTP route and target group configuration, whereas this infra specific resources, it will stay outside. So this HTTP route and target group configuration, those are the infra specific resources. I am keeping it outside because these are environment specific. This is not something related to application specific, right? So this is how you will do in the production as well. So, and there will be a cleaner GitOps approach. So now whenever the CI part will be done and the CD should be triggered, right? So how this Helm and HTTP route and target group YAML will be combined, because the CD means continuous deployment. So it should reconcile automatically. How this both can be deployed at the same time, and this is where customize comes in. So ArgoCD has built-in support for customize. So it renders both your custom manifest and the Helm template. So it both combines and deploy. So we need to create a customize config file as well. And after creating the customize YAML, we will push that to GitHub repository. So I'll show you in a better way. So this is the diagram I have. See, our application is packaged in Helm, and we have different manifest for HTTP route and target group configuration. So now we'll create a customized.yaml file. We'll push that to GitHub repository. Once the CI part is done, then the CD part will get triggered, and then ArgoCD customize combines both the template and it will render as a single unit, and this is how it will deploy in the ArgoCD. I hope this is clear. And the customize YAML file, will keep it in the root directory. Let me show you how the customized file will look like. So here is the customization.yaml. So this is the file we have. Here in the resources section, you see I have kept HTTP route and target group configuration. So it will pick from the appropriate directory, and I have also given Helm charts. So the repository link I have given, the version and the release name. Rest of the things I have given, like namespaces and values file, all the things I have given over here. So the customization.yaml file, it will combine both the Helm charts and the manifest, and it will render it as a single unit. So when we'll create the ArgoCD application, that points to the customized directory. So this is the customization file we have. So when we create the ArgoCD application, this points to the customization YAML. So ArgoCD repo server clones the Git repository. So ArgoCD has repo server, the UI server. Then it runs something equivalent to customize build, so that this will build automatically. This will combine and this will build automatically. And this sends the render manifest to the Kubernetes API. So all of this happens inside the ArgoCD. To do all this, we need to create the ArgoCD application. So I am in the Bastion host. Go inside ArgoCD, and here you will have the ArgoCD app. So we'll deploy our microservices application as a ArgoCD application, so that developer, QA or other engineers will have the access to the application, right? So they can view what's going on or what not. So this is the YAML file. So the kind is application, then we are giving the metadata, namespace we are keeping it in ArgoCD. So here the spec project is default, and the source we are giving the repository link over here, and then destination we are giving the Kubernetes default SBC, specifying the namespace which is boutique app, and sync policy automated, and it will create a namespace. So this namespace is not available right now, so it will create the namespace. So this is nothing but what you do here. Once you deploy the ArgoCD application, so you create the application over here, right? New app, then you give all the application name, project name, and then here you give GitHub repository. So this is the same thing, but we are doing in code. This is basically the same thing what you do over there. So basically it tells ArgoCD what to deploy, from where, and how to keep it in sync, right? So it will take this GitHub repository as a source of truth, and it will continuously deploy our boutique app from the Git to Kubernetes. So this is called a GitOps approach. So here we are giving a target revision head, so that it will pick the latest commit, and the path it will take the root directory. Dot means the root directory where our customized file exists. So the ArgoCD will read customization YAML, then it will go to Helm, then the other like HTTP route and gateway configs, like target group configs. So those it will take from this root directory. And that destination is our cluster, as I just explained, meaning the current cluster. If you want to deploy it in different cluster, then there will be separate endpoint for that. And namespace is target. So here sync policy is automated, prune is set to true. That means it deletes the resources which is removed from the Git. And we are enabling the self-healing. If someone changes the cluster manually, so the ArgoCD automatically fix it. And at last we are mentioning the namespace. If the namespace doesn't exist, then it creates that automatically. So now let's go and apply this. kubectl apply -f boutique app YAML. So the application is got created. Let's verify that in the UI. See, it's automatically created and it's completely synced and is still progressing. So it took all the things from the GitHub repository, add service, card service. So these are the services, then service account, and then this is the deployment. So the customization file automatically picked and combined and deployed it. So we already have HTTP route and app tg config ready. So you don't need to apply it manually. If you are applying it manually, then also when you deploy the ArgoCD app, it will automatically deploy it again. We saw how customization work, how Helm and the custom manifest are combined together. Great. So now if I head to Route 53, as there is a host requirement, so the external DNS should have created a DNS record for the application. You see, it's already created the record automatically. We don't need to create the records manually. Adding the DNS record part is handled by external DNS, right? So if I just simply go to the browser and type app.devops.site, I should be able to access the application. And that's too with HTTPS. So you see, our application is ready. I can add to cart and then I can place the order. So our application is working. Now there is one more thing. If you see the front end pod, if I check the images, it is taking version 0.10.4, right? But if I go to my packages, let me see the packages. front end. You see over here, this is the oldest image, not the new one. So the new one is this one, which is the current tag, but this one is using the older one. If I go to the next one, maybe the add service, this is also using the previous image, I mean the oldest image, not the new one, right? Why so? Because in the current setup, the CD part, which is ArgoCD, it never takes the updated image from the CI. We need an image updater here, so that whenever there will be an update, so there is no trigger point, like CI part is separate and CD part is separate for now. So we need something, so whenever there is a code change in the GitHub repository, so the CI part will trigger automatically, and that's what it is happening right now. So that part is done. So we need something when there is a new image, so the continuous delivery will get triggered automatically and then update the image over here. So we'll deploy the latest image every time. So whenever the CI part is done and the image is pushed to the registry, the same image tag should be automatically updated in the Helm value file. After that, rest ArgoCD can do its job. And that's where Argo image updater comes in. Let's understand what ArgoCD image updater actually does. So basically, it watches your container registry. That means this is your container registry. It watches the registry, and when a new tag appears, it updates the image tag inside Git. Commit the changes and ArgoCD syncs that automatically. So there will be no kubectl, no manual deployment. It's pure GitOps. I'll also give some documents so that you can read it more. So just check the readme file. I'll also provide the documentation. And this Argo image updater will install in the cluster. So one more thing I just want to update, that ArgoCD image updater can work in two different modes. One is live state update, which is also called ArgoCD API mode. One is Argo API mode, which is also called live state update, and another one is git write back. So we will use this one. We will use this. We will not be using git write back. So what is the difference between these two? Let me explain you what is the difference between these two. So this uses the CRD called image updater, and the update strategy will be newest build, so that whenever there will be a newest build, so it will pick that update. So images are updated via ArgoCD API, so there will be no git write back. That means, let's say you pushed the image is called version 02, so this image is got pushed. Now if you are using git write back, this tag will be write to the deployment file. So the deployment file will get updated, so automatically ArgoCD will get updated. So this is one method which is git write back. So it adds an external commit. So this is called git write back. Whereas what Argo API mode does, it basically update the state live. It doesn't do anything to Git. It just look at your package registry, and it find out there is a new image has been updated, and it directly update the manifest inside ArgoCD. It doesn't go back to your GitHub and add any extra commit. So this is the basic difference between these two. We will be using this because it is simple to set up, and in production also you will mostly use this one. So for git write back, as it adds the newest tag to the deployment, so it needs your GitHub account permission. But whereas in Argo API mode, because it doesn't do anything to your GitHub account, so it doesn't need any permission. If you want to pick git write back, then you can definitely choose this one, but it requires some additional permission. You just need to give some read and write permission. Let's come to our cluster, and we'll deploy the Argo image updater, right? Let me add the repo. So I'll be using Helm to deploy that. Let me add the repo first, Helm repository. So this is already exist, so only it's skipping. Now let me install the chat. I'll go one step back, and here you have the updater values YAML file. So I haven't changed anything. You can simply Helm install and deploy the Argo image updater, but I already have this. So in this I have given better name and all, so you can just simply refer this file. So I'll be installing this ArgoCD image updater in ArgoCD namespace, right? Let's verify. Let's wait for some time. Yeah, now it is running. Our CRD installation is done, right? So we need to add the image updater YAML. Let me just explain you what the image updater does. Where is it? Let me just scroll down a bit. Yeah, so here I already have added the documentation. If you want to read, you can just go ahead and read it, right? And yeah, if you are if your repository is private, or you are doing the git write back method, then you can follow this step. So basically you need to give the permission to the path, and you need to create a secret, and while deploying that, you can just add this secret, right? And that's all, it should work. So basically I had added this secret in that file, so only I used this. Otherwise you can just go ahead and do this as well. So I didn't have the secret exists. Let me just upgrade without the file mentioning. Yeah, there is a typo. Yeah, let me just quickly verify whether it is running. Yeah, it is running. It didn't update though, but yes, it is running. Let's move forward. So this is the image updater custom resource what we have. So the purpose of this file is to auto update Kubernetes manifest whenever the new images are available in the GitHub container registry, right? So this config is for ArgoCD image updater. It automatically updates your app images whenever there will be a new version is pushed. So the kind we have image updater over here. This tells your ArgoCD image updater how to track and update the images. This is the target application. So whenever then it finds the pattern boutique, it targets that, right? So our application name is boutique app. So whenever it finds some application, like the application reference over here, right? So here if you see, this is the application name. So it targets to this application. If you want multiple, then you can definitely provide multiple applications. Then here in common update settings, we are giving update strategy to the newest build. So whenever it finds the newest one, it will update, and the tags are allowed at this. So there is like regular expressions, it will take only GitHub SHA commits. So that tag should match to this format, like commit SHA tagging. And these are the image lists. We have ad service, we have card service, checkout, currency. So we have all the images list. It will only affect to these images. So how it works? GitHub action, build the images, and it will push to the GitHub packages, GitHub container registry. This image updater detect the images, update the images live using ArgoCD API, and this is how the new version is deployed. Great. So let's go ahead and deploy this image updater.yaml. It should be here only. Yeah, I have it here. Let me just do kubectl apply -f image updater YAML. Great, it got created. Let's verify. Yes. Now let's head to ArgoCD and we'll see if there is any change. Let me open in a new tab. You see, it automatically started processing something. Let's see whether if it is taking the newest version. Let me just refresh it. I think still it's picking the older one. Yeah, still is picking the older one. Let's run the CI. Now we have connected the CI and CD part by integrating the ArgoCD image updater. So let's run the CI. So how to run the CI? Whether we can run it manually or we can just change something in the source code so that the source code will get updated. And after the source code is getting updated, the action should trigger and it should build a new image and push to GitHub container registry. And then the ArgoCD image updater will take that and deploy it in ArgoCD, right? So this is what it should do. Let's go to our repository. So inside the src, let me update the front-end microservices, right? So what should I do? Let me go to a random one. Let's say this is a middleware.go, or I can simply, I edited this handlers.go, I edited this, I added these two lines. I'll just simply remove this. Oh, sorry, this is not the, I know this, like I'm not logged in with the original account. Let me just quickly logged in. Yeah, I have logged in here. Let me go to src and let's go to front end, and from front end I'll just update this handlers.go. Just remove them, remove the empty lines, and let me commit. It automatically took the commit message. We'll commit directly to the main branch. So now if we go to the action, it should trigger the pipeline. Yeah, as you see, it's running. It detected the changes and running the pipeline. Yeah, it is running the pipeline. Let's wait for some time. The tree scanning part is done. It pushed that images. Yeah, this is done. So the build is done. Let's see whether this got synced or not. So we updated the front end. Let me check the front end. Let me just refresh. Still sync it. Okay, it did not take. Let me just check the logs. kubectl logs. So it's deployed in ArgoCD namespace. Just considered 11 images skipped 0, images updated 0. Okay, we are getting some error over here. Okay, here it is throwing the error because this GHCR secret not found. Okay, so as I told you, like I have deployed with the file, but it did not get updated. So let me do one thing. Let me just redeploy the ArgoCD image updater, but without the file. So initially what we have done is, so we had updated with this file, right? But this file include a secret, which I told you includes the git write back method. So that the secret was needed, and I had added in this file. So I installed with this file. So it's saying the GSCR secret not found. So it giving me the error. So what I'll do is I'll just simply uninstall the ArgoCD image updater and install it again, but without mentioning this file, right? Let me do cubes, no, sorry, not kubectl, helm list -n ArgoCD, and I'll just simply uninstall this. Helm uninstall ArgoCD image updater. Right, it is uninstalled. Now let me install it without the file mentioning. Now let's verify kubectl get image updater. Yeah, image updater is already available. Let me just see the pods. Get pods -n ArgoCD. It's not running yet. Let's wait a bit. Yeah, it's running now. Now let me check the logs. Yeah, you see it's updating the images updated 3, it's mentioning error is set to 0. Okay, Now it should have worked. Let's go here. Yeah, as you see, the email service got updated, the front end port got updated, currency service, email service, front end, these three got updated. If you see now, it's picked the newest one. So this is the newest one in the currency service. Let's verify the packages. Currency service. Where is currency service? Here it is. And the latest image ending with 50261. 50261. See, 50261. Let's check the email service. So the email service image is taking, it's ending with 06B. Email service. Let's verify the email service. See, 06B. Let's check the front end. It's ending with DB90. Front end, yeah, DB90. You see, right? Okay, you might be thinking why it did not update add service, cart service, and checkout service. If you see checkout service, so there are no version at all. So version 0.10 is the latest one. It's picking all the latest images version, right? So yeah, let me just change something in the checkout service and let's wait and see whether it is getting automatically updated or not, right? Let me just duplicate it once again. Let me go to the repository, and this is checkout service, right? Checkout service. So let me go to the src, then we have checkout service over here, and then let me pick a random file. This I'll pick genproto sh, and let me add a comment, empty comment line over here. Simple comment over here, and commit the change. So it should trigger the CI pipeline, and after the CI part is done, then it should automatically update in ArgoCD as well, right? You can pick any microservices. You can pick front end, add service, cart service, any microservices you can pick. It should work accordingly. Let's check the action. It got triggered. Previously, the checkout service has only one image version. It is getting pushed to the GitHub container registry. Okay, it's done, right? Let me just refresh this. So I should have a new commit over here. Yeah, you can see I am having a new image versions. Now if I go to ArgoCD, this checkout service should have updated automatically. Checkout service, yeah, this is the checkout service. Yeah, just wait for some time. It takes some time to get updated. Otherwise you can just manually sync it, but if you are not doing manually, then just wait for some time. It should automatically get updated. So now as you can see, there is a new replica set for checkout service, and it's updated a few seconds ago. Now if you see here, see the latest images, it has been picked. So it is ending with 3112. See, this is 3112. So this is how a complete GitOps based application should work. So this is how you should configure your CI and CD, and using ArgoCD image updater, or you can use some other third-party tools to bridge between them. And now if we access our application should run absolutely fine, right? So there is no breaking, nothing has happened to our application. It is running as expected. So whenever there is something changed in src, and then automatically the image is built, sent to container registry, then ArgoCD image updater picks that and updated in ArgoCD. So continuous integration and continuous deployment is done. So our application deployment is done. Now what's next? We'll see how we can do monitoring, logging, and rest all. So we'll be seeing observability part next. I hope you are enjoying this. If you are doing so, then please give a nice comment so that it make me motivate to create such kind of contents. Okay, all right. Now let's move to our observability part. Great. So in this monitoring stack, I'll be using Prometheus as the primary data source. I mean, this is the only data source we are using, and Grafana for visualization, and Alertmanager for handling our alerts, and the Slack will be configured as the notification receiver. So whatever alert will be getting generated, that will be delivered to the Slack channel, right? And we will visualize the complete application metrics along with the Kubernetes components and supporting workloads through the Grafana dashboard, right? And here I have even mentioned that we generally don't manage the observability stack by ArgoCD, because anyone having the access to ArgoCD can modify it. As I explained while I was explaining you the architecture diagram, so only our application will be exposed, I mean will be deployed as a Argo CD application, because generally the QA engineers or the developer, they need to see like how the application is running, so we can just give them the Argo CD endpoint and they can access and they can see the status of the pod, the deployments and all. But this observability stack like our Grafana, Prometheus, in logging we have Kibana and all, so we'll be not deploying as an Argo CD app, because that we manage as a DevOps engineer, as an administrator, we only manage the observability, right? Prometheus, Grafana and all we will be doing, so we'll be not deploying as an Argo CD application, right? So first thing first, we need to create a namespace, which is monitoring namespace. Let's go and create that. So I'm using this kubectl very repeatedly, so I'll set an alias for it. Great, we have the monitoring namespace ready. Now let's set up the Slack channel. So you need to go to this API slack.com/apps. So I already have given you the information over here. You can just right click and open the link. It will ask you to sign in to your Slack account to create an application. I'll just sign in with Google. So these many workspaces which I have, I'll just create another workspace for this project. Let me call it DevOps doc. Let me call it DevOps doc, okay? With all the capital letters. I'll keep it, I'll keep the profile photo as it is. I'll skip this step. Let's start with the limited free version. Great. Let's create a new channel. Click over here, add channels, create a new channel and give the channel name as, let's say I'll give it Alertmanager, because we want the alerts to be delivered in the Slack channel. So this will be the channel where we are receiving our alerts, right? Click on next, keep it public. Then it asks you to add some people. I'll skip it for now. Great. So we have our channel ready. After this is done, go to the same URL again. Now it will ask you to create an application. Click on create an application. Now just click on from scratch, and in the app name you can give any app. For better convenience, I'll name it as Alertmanager. I'll select the workspace, then create the app. Great, our app has been created. So these are the basic information. Now let's go to incoming webhook. So here it is the option called incoming webhook. Go to incoming webhook because we need to create the webhook for that. Turn it on, then little bit scroll it down and add a new webhook. Once you click on the new webhook, it will ask you to select the workspace and the channel. I'll choose the Alertmanager channel, right? And allow it. Great. So we have our webhook URL ready. You can just copy this and paste it somewhere else. So refresh this page, you will not be able to access this, right? So I'll copy it and I'll paste it in my notepad. So before publishing this video, I'll just revoke this webhook, or I'll just simply delete it from here. Shouldn't expose the real Slack webhook URL in your messages, right? Because anyone can now send messages to your Slack channel if you just expose it publicly. So we'll be storing this in the Kubernetes secret instead of plain text in the values YAML. Before deploying, we'll be just creating a secret, and using the secret only, we'll be passing the webhook. Then we'll mount the secret into that pod, right? Great. So this part is done. So now let's go and create a secret. So I have the command ready here. Just copy the command, paste it here. So we are creating a secret. The secret name is Alertmanager Slack webhook. We are creating it through CLI commands, and here we are providing the webhook fully qualified domain name, right? And we are creating it in monitoring namespace. I'll copy that again. Great. Hit enter to create that. Now let's verify. It has been created. Now we will deploy our kube-prometheus-stack. So in the stack, basically we'll be deploying Alertmanager and Prometheus, Grafana, everything will be deploying as a stack called kube-prometheus-stack, and we'll be deploying that through Helm, right? So let's add that repository first. So this is the command to add the repository, Helm repo add. So basically this thing you will get it from here. If you go to artifact hub IO, here only we'll get it. All the Helm chart I have deployed, I took that from this platform. So this is the platform for the Helm chart. Prometheus stack. Yeah, this is the one. This is the official one. You can see it has 1.19k star. So here you can just click on install, and here you will find the command to add the repository and to install the chart. But for your better convenience, I have added it in the readme file. You can copy the same from here as well. So let us get the Helm values and save it in a file, and we'll edit some values over there. But I have already done it for you. Let me add this repository first. If you go inside the repository, and here we have observability. You see over here observability. Just cd into that, and here I have Helm values. I'll show you what I have changed over there. So basically how you will get that file, just execute this command Helm show value, so it will show the values, and we are redirecting it to a file called this. So similarly you can see, yeah, kube-prom-stack, I got this file by executing this command. Now I need to edit this file. Let me open that file first. Now we have to attach the secret which we have just now created to the Alertmanager section. So basically we'll attach the secret to the Alertmanager spec so that it will mount to the pod, right? Let me search Alertmanager. Press N for next, or better I'll type Alertmanager spec. Alertmanager spec. Yeah, here it is. I found. Then just scroll down to the secret section. Yeah, here is the secret section, and here as a list I have provided the name of the secret, Alertmanager Slack webhook. Then after this, go to Alertmanager section and find its config block. So let's type Alertmanager. Click next. Yeah, this is the Alertmanager section, and here we will just scroll down and find the config block. This is the config block. So this is the space where we will set up our alert manager. That means who will be the receiver, what is the target, and what will be the route. So everything will be specifying over here, right, in the alert manager config section. So basically it controls how alerts are grouped and how it is routed and sent to the Slack channel. You can definitely configure Teams or email, like other endpoint you can definitely configure, but here we are configuring with Slack, right? So now let's break down line by line. So this is the global setting. So it will just wait for 5 minutes before making an alert as resolved. So as you can see in global, I have kept it resolve timeout to 5 minutes. This is the configuration. Just before that you will find the the link, so that you can just visit this link and read about the configuration. And by reading this documentation only, I did this configuration setup, right? So now we have routing rules. Just ignore this. I just kept it default. If these are not that much needed, I'll just jump to the route section, because this is the part what we are configuring. And here I am just grouping it by namespace, and the wait before sending an alert is 30 seconds. The interval time is 5 minutes, and the repeat interval is 12 hours. So it will resend the same alert every 12 hours if it is not resolved. The default receiver is set to Slack notification. So in the route we have sub route section, and this is where you will be specifying Slack notification. So the receiver is Slack notification. This is the default, and here in the route section you will be mentioning the same. And the matcher, I have kept it severity is equal to critical. So it will only alerts with this tag. If an alert level contains this label, severity is equal to critical, it goes to the Slack notification. In our case this is redundant, because the default receiver is already Slack. So in real setup you might see the critical will be sent to pager duty, so the engineer should get a call, or the warning will be sent to Slack, or the information will be sent to email. So there will be different setups for that. Then here we have receivers. So this basically defines where the alert should go. Now here we will route the path basically. That means in the particular tool where should be the subroute kind of thing, right? So it defines the actual notification method. Here again we are mentioning the Slack notification, and in the Slack config and in the API URL you see over here, we are just adding the secret. So instead of hard coding the FQDN, you are just adding the secret, and this is the best practices. So here you are mentioning the secret, and from the secret it will pick the API URL, which is the Slack webhook URL, right? And the channel name is alerts, but here the channel we provided is alert manager. So here the channel we have kept it alert manager. So I'll simply edit this to alert manager. And this send resolved is set to true, because once the alert fires, after the alert has been resolved, we want the resolved message as well. So it will send the resolved message to this particular channel, right? And this is the template, and this allows the custom message formatting. You can define like a custom message layout, you can add some emojis as per your need, you can just edit that. One more thing I just want to tell you, so alert manager only reads this configuration and route based on it. It doesn't decide what is critical, what is warning, and what is information. Based on your alert labels, it routes those alert to the particular channel or particular tools whichever you have mentioned. So how it actually works, let's say you have a metric and Prometheus scrape those metrics like from pods or from nodes, from other workloads, and we have alert rules defined. And when something is critical inside the kube-prometheus-stack, which we will be deploying now, there are many alert rules. You can set up your own rule as well. You can set up your own alert rule and define here as well. If you want a video on that, then you just comment down below. I'll definitely make how to create custom alert rule and how we can set up the alerting for that, right? So Prometheus, after that Prometheus says if this condition is true, like severity is equal to critical, if that condition is true for that particular metric, then attach that label and create an alert, and Prometheus sends the alert to alert manager. And here when the conditions become true, the severity is equal to critical, this condition is become true, or let's say you have another labels like some pod is crashing, or if you want if the namespace is set to production, then send this alert to Slack. So Prometheus pushes this to alert manager, and based on the route labels, alert manager checks and send to Slack notification, which is this channel. This is very simple. I hope you got some idea how this is being routed or how the Slack is being configured. I'll just save it, and this is the only thing you have to set up here. For the alert manager, we'll definitely set up other things, but for now this is the only thing you have to do the setup. Now let's install the Helm chart. So this is the command I have, helm upgrade -i for install kube-prometheus-stack. Then this is the path where the Helm chart is available. Then this is the version, and this is the values file we are mentioning over here, and this is the namespace. I'm already in Helm value, so I'll just clear this out. So whatever I just explained you, the same thing is already explained in the readme file. So already available in the readme file. You can see everything is already, yeah, you can see over here. See, everything is already explained, right? I'll just hit enter to deploy it. It's taking some time. Let's wait for 2 to 3 minutes. It shouldn't take much time than that. Great, it is deployed. Let's verify. kubectl get pod -n for namespace monitoring. Yeah, all of them are running. Let's see the services as well. Great, everything is set to cluster IP and services are also available. Let's see our Slack channel as well. See, we got one alert firing message, which is a kind of integration message on Slack. Okay, so this the first alert we got. That means our configuration and all are correct. So just wait for some time. Once this is resolved, you will get the resolve message as well, because we set the resolve is equal to true. That alert part is done, but we haven't exposed our Grafana and Prometheus till yet, right? Now we need to access the UI of the Grafana and the Prometheus. So in this Helm chart, it doesn't include the HTTP route and the target group configuration. As we know, when we need to expose something through gateway API, we need additional component for AWS load balancer, such as HTTP route and target group configuration, right? And we are doing that since ArgoCD deployment. So we created additional HTTP route and target group configuration for ArgoCD for our boutique application, which is our microservices application. And to expose Grafana and Prometheus as well, we need both the configuration files, which is HTTP route and target group configuration. So this Helm template has not included those configurations. So we need to explicitly add that configuration, right? So we'll write the manifest file manually and manage it externally, right? I already have created. If you go one step back, in the observability directory, I have the HTTP route Grafana and HTTP route Prometheus ready. Similarly, target group Grafana and target group Prometheus ready, right? Let me open it. So this is pretty straightforward. I already explained what does this HTTP route and target group configuration do, so I don't need to explain it again, right? So this is doing the same thing, but here in the host name I kept it this host name. Like, okay, here the host name is a bit wrong. I'll just edit it simply. Vi HTTP route Grafana. So here Grafana, then the host name I'll be mentioning over here, which is DevOps.site, right? And rest all are the similar thing. The parent reference I have mentioned the gateway, and here app ALB gateway, which is our primary gateway, and I am keeping it for HTTP and HTTPS both. And in the backend reference I am giving kube-prometheus-stack Grafana, because this is basically, sorry, kube-prometheus-stack Grafana is basically the service for Grafana, right? If I go up, you can see this kube-prometheus-stack Grafana, the same thing mentioned here, kube-prometheus-stack Grafana, right? All right, let me view Prometheus as well. Not Prometheus, sorry, target group Grafana is the same thing. Target reference is this, and default configuration is IP. This is good. Now we'll apply both the file. To apply, do kubectl apply f http route grafana.yaml. It is created. Now we'll apply the target group configuration as well. Great. Both of them are created. You can simply verify it. kubectl get http route -n monitoring. It is available. Similarly, you can verify the target group configuration as well. So we have external DNS ready over here. So if I take this and hit it in the browser, I should be able to see the Grafana UI. Yes, you can see. If you verify over here, then here also it should have added the Grafana record. See, this has been added. Just wait for few moments. Takes a bit time to complete. Yeah, it came now. So the default username is admin, and to get the secret, it gives you some command: access Grafana local instance, get Grafana admin user password by running this command. So when you deploy it, it gives you some command to get the admin user password. So I'll just copy, or you can just get it from the documentation as well. Documentation in the sense the readme file. There also I have mentioned. So here I'll just get the password. This is the password. Copy it and then paste it over here and log in. Great, we have logged in. Here now in the, if you go to drill down, here you will get all the metric logs and all. So as we have Prometheus database connected, so we can see the metrics over here, right? On metrics, then here you can see all the available metrics. And in the kube-prometheus-stack, we have something called kubestate metrics and node exporter. So basically it exports the node metrics, and kubestate metrics, it exports the pod metrics and created a ready-made dashboard for you. So here if you go to dashboard, and here we have all the dashboard ready. If you go to networking pod, then you can see all the pods metrics and the dashboard ready for you. So you see these different panels. You don't need to create anything manually. So that is the beauty of kube-prometheus-stack. So every dashboard you will get it here. Let's say you want to see compute resources, pod wise compute resources. If you want, then here you just select the namespaces and select the individual pod and see how they are behaving. Let's say we have boutique app, and in the application you see ad service, cat service, and front end we have. So everything we can see it here, right? Don't need to create any dashboard manually. Great, this is great, right? And accordingly you can set the alerts over here as well. Now similarly, let's expose our Prometheus as well. To expose Prometheus, again I have the HTTP route for Prometheus and target group configuration for Prometheus as well. Let me see HTTP route Prometheus. Yeah, so I'll just quickly edit the host name. This host name is incorrect. DevOps.site. Everything stays the same. I'll just quickly check the target group configuration. It should be good only. Yes, this is good, and it is pointing out to the right service, right? kube-prometheus-stack Prometheus. Yeah, kube-prometheus-stack Prometheus, correct. Let me quickly apply both of them. I'll apply Prometheus, HTTP route Prometheus, and another one is target group configuration. Verify. Yeah, we have target group configuration for Grafana and Prometheus ready. And let's see HTTP route as well. Yeah, HTTP route is also available. Now we can just access it directly in the browser. Great, we can access it. You can just simply click over here and explore the metric. So this is all the metrics we have available inside the cluster, right? Every metrics we can see it over here. The metrics you saw just now in this drill down metrics tab, the same metrics are available here. So basically Prometheus is passing these metrics to Grafana, right? And Grafana is fetching from Prometheus, right? Great. So this is the monitoring stack what we have now, and I have shown you Prometheus, Grafana, Alertmanager and Slack configuration. Now the next part is logging, because in observability we have two sections, one is monitoring and one is logging. Tracing you will use very less, so that's the reason I haven't shown you the tracing part. If you want a dedicated video on tracing, just let me know in the comment section. I'll definitely try to make a video on it. But now let's move to the logging part. For logging we are using EFK stack, Elasticsearch, Filebeat and Kibana. For Elasticsearch for data source, Filebeat to ship our logs to Elasticsearch, and Kibana is for visualization. I am not using Logstash over here because Logstash is quite heavy. I only need the logs to be shipped from the pods or nodes to Elasticsearch, and from the Elasticsearch Kibana will get all the logs from the Elasticsearch like I showed here. Let me open the diagram quickly. Right, so this monitoring part is done, boutique part is done, this is so done, and here we are doing logging. So here if you see we have ECK Operator, and in that we have Elasticsearch, we have Kibana and we have ECK Filebeat. So Filebeat, let me put it in a different way because it's very hard to see. This is better. If you see over here, then we have Elasticsearch, and here from our application Filebeat will ship that log to Elasticsearch, and from Elasticsearch Kibana will take that log and we can visualize those logs through Kibana, and Kibana is exposed through Gateway API, and this part and all we already have completed. ArgoCD we have completed, both CI/CD is done, and yeah, monitoring part is also done. So only the logging part is pending and this load generation part is pending. Rest of them are already done, right, as you can see over here. Great. Now let's move to the logging part. So as I said, we'll use Elasticsearch for log store, Filebeat for log shipping and Kibana for the visualization. So there is one more thing which is called EBS CSI Driver. So we need the EBS CSI Driver as an EKS add-on for Elasticsearch to dynamically provision the EBS volume. So what is the EBS CSI Driver basically? So it's a Kubernetes plugin that allows your cluster to create and manage AWS EBS volumes dynamically. So this is very specific to EKS, right? So why we need this? Kubernetes by itself doesn't know how to talk to the AWS storage, right? So it needs a kind of a bridge. So your EBS CSI driver, it's basically the bridge between Kubernetes and AWS EBS. EBS stands for Elastic Block Storage, which we attach to the EC2 instance. So what is the problem without EBS CSI driver? Imagine you run a pod which needs some kind of storage, which will store something. So basically we can attach some storage to the pod, we can mount it, but when the pod will get deleted, data which is stored in the pod, that will also get erased, right? So to get rid from that, we need some external volume. So our pod needs the volume, but Kubernetes doesn't know AWS, and for the volume we will require EBS volume, so that when our pod will get removed or get crashed, our data will be safe in the EBS volume. In this case, without CSI driver, we have to manually create EBS volume, we need to manually attach to the EC2 and manually mount to the pod, which is not scalable, right? So the solution is the CSI driver, EBS CSI driver. These all the things become automatic. So what does it do? It dynamically provision the volume, which is the EBS volume, and mount it to the pod and node. So basically it attaches the volume to the correct node and detaches when the pod moves to another node. So everything like the life cycle handles automatically. And as I said, even if the pod dies, the data remains safe in the EBS. And it also provides the scaling support, like multiple pods will have multiple volumes automatically. So that is the power of EBS CSI driver. In our project, we are deploying Elasticsearch. So Elasticsearch needs a volume to store the logs. So for that, we'll be going to deploy EBS CSI driver. So if there is any requirement, EBS CSI driver will go to AWS and provision an EBS volume automatically and mount to the node where our Elasticsearch pod has deployed. So ultimately our pod will have that access to the EBS volume. So it provision, attach and manages the AWS EBS volume for our Kubernetes workloads such as Elasticsearch. If you want some other, then it will automatically provision it, and it enable the persistent storage. And that's what this EBS CSI driver does. So you can follow the below steps for the EBS CSI driver installation. So we'll add the add-on to the EKS. I'll just first describe the add-on versions for the AWS EBS CSI driver. This is the version. Now list the versions. Replace the cluster name. As you can see, this is the add-on version we have, and this is the current list of add-ons we have in the EKS cluster, right? So the AWS EBS CSI driver that needs some IAM permission, so we'll create them first using EKSCTL. This is the command basically to create an IAM role and attach a policy. So this is the policy what we have, Amazon EBS CSI driver policy, and this will create a role with the service account, right? Let me just replace the cluster name. Great. Let me just hit enter. So that command created a role. Let me just find out the role name. I'll go to IAM, or you can just go to CloudFormation. You could have give a role name over there, but I forgot to give the role name. So the automatic generated role name would be different. To create the add-on, we need a role. This is what we created. Let's see the outputs. Yeah, so here you can see this is the role. This is the role ARN, right? So now we need to create the add-on. As we don't have the add-on, so we need to create the add-on. I'll describe the add-on version again and the name of the add-on, right? Now I'll paste the command to create the add-on, and here I'll just replace the ARN of the role. This is the ARN. Here you need to paste the role ARN. Right, now here you need to provide the name of add-on. So the name of add-on is this, AWS EBS CSI driver, and the cluster name you need to provide over here. Which is Terraform cluster. Great, this is the command. Hit enter. Great, it has created the add-on. Let me list again. Yeah, as you can see, the add-on has been added. Now let's verify. Yeah, as you can see, it is deployed, the EBS CSI controller and EBS CSI node, and all of them are running. Let's see whether it has picked the role or not. Let's describe this. kubectl describe pod. I'll grab for role. Yeah, as you can see, the role ARN it has picked, right? Great. Now we'll create a namespace for logging. The namespace is got created. Let's install the ECK operator. So what is an operator basically? Let me explain you what is an operator. I'll explain what is the operator, then I'll go to the ECK operator, right? So an operator is a kind of a controller that automates the application management. In a simple term, so instead of you deploy or you do some manual work, operator does it automatically. So without operator, you will install the app, you will configure it, you will scale it, will handle the failure. But with operator, you only configure the operator will handle the application. So that's what the operator do. So it uses the custom resource definition, it watches the cluster state and take the action automatically. And what is ECK operator? So ECK stands for Elastic Cloud on Kubernetes, and we will install ECK operator, right? And here I have given you the documentation of the Helm chart. You can simply go there and you can follow from there as well, right? It's the same link which is Artifact Hub. You can take the chart from here as well. So ECK stands for Elastic Cloud on Kubernetes. So it manages all the Elastic components such as Elasticsearch, Kibana, then all the bits like Filebeats, Heartbeats. So all the tools it has in the bit section, it manages all the tools inside Kubernetes. And why ECK is needed? So without ECK, you have to manually install Elasticsearch. You have to manually configure them. You need to make sure they are healthy. Same goes for Kibana and bits as well. With ECK, ECK manages all the things automatically. And once you install the operator, we need to install the ECK Elasticsearch, ECK Filebeat, ECK Kibana. We have installed the operator, right? Now we have to tell the software which it needs to manage. So you need to install ECK Elasticsearch, ECK Filebeat, and ECK Kibana, which I have shown you in this architecture here as well, right? And what does this ECK Elasticsearch do? It stores the logs, metrics, and data. It supports search and analytics, and it is kind of a distributed system. And what does this ECK Kibana do? It visualizes data from the Elasticsearch. It has the dashboard. It has the graphs and logs, same as Grafana. And ECK operator handles the deployment. It makes the connection to the Elasticsearch. It handles all the configurations. We don't need to worry about that. So inside this bit, we need to configure. We are using Filebeat. It collects the data from the system such as this application. It collects the data from the system and it sends to Elasticsearch. So it will collect the data from here, it will send to Elasticsearch, and from Elasticsearch Kibana will gather. In the Kibana we will see all the logs, we will see the dashboards and all. So basically the developer, we will provide them the Kibana endpoint, so they don't need to go to the cluster to just see the logs. They will have the Kibana endpoint, and in the Kibana they can see all the logs and dashboards and all, right? So that is the whole idea. So ECK handles deployment and beats Kibana, Elasticsearch. It handles configuration. It has the integration with Elasticsearch, right? Let's go and implement. So as we already installed the EBS CSI driver, we need a storage class. So what is storage class? So basically a storage class tells Kubernetes how to create the storage automatically. So there are multiple types of EBS volumes, right? When we need a storage, when we need something from AWS EBS, we need to tell Kubernetes, okay, we want this kind of storage for our application. So how do you tell that? That's where storage class comes in. So without it, you have to manually create and attach as we discussed. But with storage class, you will provide what kind of storage you want, who will be the provisioner, what will be the reclaim policy, and what will be the volume binding mode. These all the things you need to mention in the storage class. And here also we have mentioned that this storage class will be the default storage class. So default class is true, set to true. So by default Kubernetes has a entry storage class, but it will not provision any dynamic volume in AWS, right? If I show you, I'll just type kubectl get storage class. See, it has GP2 storage class, right? But it's a entry storage class, so you will not be able to provision a volume dynamically. Let's create the storage class. So this is already available inside observability, and the file name is storage class. So I'll go and apply that. Apply -f storage class. Great. Let me get it again. So yeah, as you can see, we have it default. So now let's install the ECK components which the operator will manage. So let's install the ECK operator. Helm repo add. I have added the repository. Now install it in the logging namespace. I don't have any values file for this. I'll run this as it is. Now let's see. Yeah, the pod is running. The operator is running. Now let's install the ECK components which this operator will manage. So first I'll install ECK Elasticsearch. Copy the command from the documentation. Alright, I'll install ECK Elasticsearch in the logging namespace. Same thing, you can find it here as well. If you just go and type ECK Elasticsearch, see, we have it here. This is the same thing which I am deploying over there. Let's verify if the pod is running. So it's in initializing phase. Let's wait. So as we have installed EBS CSI Driver, and as I told you, Elasticsearch will require an EBS volume to store the logs, right? So by that time, EBS store should have provisioned a volume and mount it to the pod, right? Let's verify. kubectl get pb. Pb stands for persistent volume hyphen and logging. As you can see, 90 seconds ago, it created a persistent volume. You will find PBC as well. So PBC requests this volume and PB is the volume itself. So you can see this PBC is bound to, this is the PV. This is bound to this volume. Our pod should be in running state now. Yes, the Elasticsearch is running. Now let's install the ECK bit for shipping the log. So we have the log store ready. Now we need to send the logs to here. I need to configure the ECK bits as well, right? We need to configure the ECK bit because we need to configure that it should take the logs from certain application and send it to Elasticsearch. So that part we need to configure. So to do that, we need to grab the ECK bit values file. I should have mentioned the same thing in the documentation as well. This is ECK bit. So this is the command from which you can grab the values and redirect it to a file called ECK bits. So I have already available this file. So it should be in the Helm values directory. Yeah, ECK bits I have. Let me open it and I'll show you what changed I have done there. So you need to tell the Elasticsearch reference, right? So let me just go to the parameter called Elasticsearch ref. Yeah. So here you need to provide the name of the Elasticsearch, and the same name is available here. I'll show you. kubectl get Elasticsearch. It should be in the logging namespace. Yeah. So you can see the health is green. There is one node and it is ready. So this name you should be mentioning here in the values file. Then only the ECK bit file will recognize the Elasticsearch, right? So I have given the name over here. Then the next is the type of the bit, because Elastic has multiple type of bits. One is file bit, one is called hard bit, and another bits are there. So I'll find type. Yeah, type is set to file bit. Types of, you can read this. So there are file bit, metric bit, hard bit, audit bit. So these many bits are already available. From that bit we need file bit. So you need to mention that as well. Then it will deploy as a daemon set. If you know what is daemon set, so daemon set is basically in every node there should be one pod running. File bit needs to grab the logs from all the nodes and all the pods, right? So it should be running in every node as an agent kind of thing. So we'll make sure that it is running on every node. For that we will need daemon set. So we'll just search daemon set over here, daemon set S capital. So we are providing daemon set over here, right? And the service account is by default is set to elastic bit file bit. Is the service account here in the daemon set in the pod template. So first thing first, we have the security context, and here it is running as a root because we need the host access to grab the logs from it. And after that the service account is fine, and auto mount service access token is true. This is the default and we are not gonna touch them. In the containers the name is filebit. So the env, the name is set to node name, which is the current node, and this is used for the log discovery, and from this field path it will take the node name. So on like where the pod is running, it will find the node name first and grab the logs. From where it will grab the logs, basically we are mounting to this path, and in this path the logs are get stored, whether it will be the node logs or pod logs. In this path the logs are getting stored. So this is the mount path and this is the name we are giving. So this is for container, this is for pods, and sometimes it stores the container logs in this directory. So we are making sure we are fetching the logs from all the content, all the paths, so we'll not miss anything. And these are the volumes. Yeah, these are the volumes. So this basically deploys the Filebeat on every node to automatically collect Kubernetes pod logs and send them to the Elasticsearch using ECK. Then next we have something called auto discover, which we need to configure. So inside the config section, if you see, this is the config section, and inside that we have something called auto discover. So it automatically detects the new pods. The type is Kubernetes and hence is enabled. That means there will be no manual config needed per app. It will auto discover new nodes and new pods, and these will be the path for the logs. Then we already have mentioned the service account. So this is the service account we are creating, and the same service account we have added in the daemon set part, right? So this is the service account, and we'll make sure the service account has the right amount of permission. So for that we have something called cluster role binding, which is bind to that particular service account. This you can see over here, and we have the cluster role for that. So we are giving the access to events, pods, namespaces, nodes. So we can do get, watch and list, right? So we are giving the proper access, which means we are giving the proper role based access control permissions. So I hope you got some idea, right? When you deploy, just make sure you are configuring and your values are matching to these configs. Even I have updated the same in the readme file. Now let's install the ECK bits. So I'll do Helm upgrade, install ECK bits, elastic. This is the path basically. Then this is the version, and I am taking the values file. I'm taking the values file from here, and we are deploying it in logging namespace. Let's see whether the pods are running. It is in pending state. Why it is in pending state? Let's describe. So it says no nodes are available, one insufficient memory, one nodes didn't satisfy. Okay, so there is no place at all to run this. So what I can do is I can increase the nodes in the node group. Currently we have two nodes, kubectl get nodes. Yeah, currently we have two nodes. So let me add one more node. So basically we have much more workload, so that it will have some space to deploy this. I'll do it in the UI itself. Let me go to this node group, and I'll make sure the desired size is set to 3. Alright, then save the changes. Let's wait for some time. This will take some time to provision the node and join the cluster. Let's wait. As you can see, there is a new node comes up and it's joining the cluster. Alright, let's check the pod now in the logging namespace. So one is running, still these are pending. Let's see whether some pods are moved to this node. I'll simply describe this. Only this Filebeat is running here, and kube-prometheus-stack node exporter is running on this. It takes some time to come up. Otherwise you can do one more thing. Instead of manually placing the workload to this new node, you can just do one more thing. Directly go to here and edit this, make it 0, so that all the workload will be in pending state, and again make it 3, so that Kubernetes try to spread all the workloads across the nodes. So currently the application which is still running on the older node, they are not jumping to the new node because they are already running in the older node. Either you can manually move those workloads to the new node, or you can do is just set it to 0 and make it again 3, so that again Kubernetes will spread it across the nodes, right? I'm gonna do that. Okay, So in the meantime, what we can do is we can just see the ECK Kibana. We'll install ECK Kibana as well, right? Similar way, we need to grab the values file, redirect it to a file called ECK Kibana, and we'll edit the Elasticsearch ref. We need to tell from where it will take the logs. So for that reason, we need to give the Elasticsearch reference to this. I have kept the same thing in the file. Yeah, if I search here Elasticsearch ref, yeah, you can see I have give the reference of Elasticsearch. This is the only change you need to do. And one more thing, we need to expose this Kibana, right? So again, we have to write the HTTP route and the target group configuration. So after installing, we'll write this HTTP route and the target group configuration for Kibana so that we can expose through Gateway API. Great. It's already available in the same directory, Observability, target group Kibana, and HTTP route. We can just simply apply them, right? Let's go and apply them. I know the nodes are not came up yet because we haven't set the digest size, but let me deploy it so that when the node will come up, it will automatically get deployed. So I'll simply apply -f HTTP route Kibana. Let me verify it first. vi HTTP route Kibana. Yeah, we need to change the host name. This is the older one, so our host name would be kibana.devops.site because this is the DNS which is available in our hosted zone. I'll simply save it, and we'll check the backend refs as well. So the name is ECK Kibana KB HTTP. Alright, I'll just simply cat it so it will be a bit easier to look both the things at the same time. Let me see. Okay, get SBC Kibana. Yeah, we haven't deployed it yet. Let me just deploy it first. Just copy. Sorry, not -n Kibana. It's -n login. Let me check the nodes. Still in disable state. Yeah, it's not healthy, so only the SBC and the ports has not come up yet. There will be no ports, yeah, because it's not healthy. So let me quickly add those nodes again. I'll make it 3, this is also 3, and I'll save the changes. Let's wait for some time till the nodes come up.
A few moments later.
You can see all of the 3 are ready. Right. Let's verify the ports as well. Qctl get ports in the logging namespace. So everything is running, and our Kibana is also up and running, right? Let's verify the bits. Qctl get bits. The health is green, and we have 3 nodes, so it is running as a daemon set, so it's available on all the 3 nodes. So type is Filebeat. This is the version, and let's see Kibana as well. Qctl get Kibana. This is also healthy, so this health will go from green to red, green, orange, and red, right? So green means healthy. Elasticsearch we have already verified, but let's verify it again. I said green, orange, and red, right? So basically it's green, yellow, and red. So yellow means there will be some warning and all. Let's see why we are getting yellow over here. Check the pods. kubectl describe. Let me describe this ECK Elasticsearch. The status is true. So we are getting some message over here. It says cannot get compute and storage resources from Elasticsearch resource generation to cannot compute resources for node set default, no CPU request or limit set. So basically in the Elasticsearch values we haven't set the request and limits. So the ECK operator cannot manage the resources properly. For our learning purpose we can ignore it. Otherwise you edit the values file and give the request and limits for the CPU usage. That's what it's saying, no CPU request or limit set. If you set that, then the health will be green, right? For now you can ignore it because the phase is in ready, but for production you should fix it. Fix in the sense, just edit the values file, go to the deployment section, and in the deployment, in the resources, mention the request and limits for the CPU usage. Great. So now we need to expose our Kibana. For that we'll apply the HTTP route and target group configuration for Kibana. I already edited that, I explained you. So this is good. Now we need to apply the HTTP route and the target group configurations. Get this is applied and the target group. So here if you see in the HTTP route in the backend reference ECK Kibana is there. Let me just verify the services. As you can see, this is the service which we are referencing in the HTTP route as a backend reference. This is the port. So this is ECK Kibana KB HTTP and the port we have is 5601. The same thing I have mentioned here and I have already applied. Let's apply the target group configuration. Great, it is created. Let's verify we have the HTTP route ready. Let's see the target group configuration as well. Yeah, that is also available. Now the external DNS should have added this record in the Route 53 hosted zone. We should be able to access it directly now. Yes, and the TLS is also configured, but why it is showing not secure? Did I mention the gateway in the HTTP route correctly? Let me verify. Yeah, I have HTTPS, then HTTP and HTTPS both are there. Gateway app LB gateway. Yeah, that is correct. Let me explicitly type HTTPS. Yeah, so sometimes we need to type explicitly HTTPS. I don't know why it's not redirecting, but yeah, it takes some time to configure it properly, but yeah, the HTTPS is working. Great. So the default username is Elastic and the password stored as a secret. Execute this below command to get the default secret. This is the default secret. When you deploy the Kibana, it will give you this command so that you can get the secret. Yeah, this is the Kibana interface. You can edit the profile and change the password. Right here, go to discover. Here you can find all the logs. Let's search for namespace here. It's saying there is no data at all. Yeah, so there is a time range over there. You just need to verify you are selecting on the right time range, right? So here in the available fields you will get the namespaces. Let's I need to see the Kubernetes container name or Kubernetes namespace. You can just go to the Kubernetes namespace and here you will find the namespaces. So the top values is logging. You can find different namespaces as well.
1 hour later.
So finally, after around 1 hour of debugging and checking the solution from ChatGPT and Claude, I finally found the correct solution from the official documentation. And after applying that particular configuration, the Filebeat is now collecting logs from all the pods across all the namespaces. So you can see here, I'm in the Kibana console, and here if I see over here, now it is picking all the namespaces: boutique app, then logging, ArgoCD, monitoring, kube system, including external DNS. So I'll just show you what I did. Let me open the bits. So let me just show you the previous version of the configuration. So in like whatever I have it in the GitHub repository, this is the older configuration of the Filebeat, but it was working previously, right? But I don't know now. It may be because I changed the cluster version, so this configuration is not working anymore, right? So what I did was I modified both the pod template and the configuration. So I went to this link, which is already mentioned in the values file. I copied it and I went to this link, because this link provide us the custom configuration. And then I try to find out the configuration which can grab the logs from all the namespaces, right? So here I went to this configuration example, and here I applied this configuration. So this is Filebeat with auto discover, and it deploys the Filebeat as a daemon set with the auto discover feature enabled. It collects logs from pod in every namespace and loads them to the connected Elasticsearch cluster, right? So this is what it mentioned. So what I did was I just took this whole link and I downloaded that file using wget command, and then I show what is the configuration, and I compared with the older configuration which is available in the GitHub repository, right? So this is the correct configuration what we have, and what I did was I copied the cluster role. So previously we had only this API groups, then we didn't have this apps and batch. If I show you in the GitHub repository, if you move little bit down, then here you will find the cluster role, and we had this. But in the documentation configuration, we have this API groups apps and API groups batch in the cluster role. So I added that, and I tried to match the configuration exactly what it is available here, right? So this ID was added, and additional configuration called this prospector, I have added this, and processor, I have added this as well, and I reinstalled the ECK bits. Then after that, when I show in Grafana, I was able to see all the logs from all the namespaces were visible. Great. So again, I'll add the latest Helm values over here, so you don't need to worry about that. I'll add it here, and I'll even update the readme file as well. So now we can see we have this boutique app logging everything from every namespaces. We have it visible. Even you can check the container as well, container image name. If you go here, you can see all the container images are visible. I'll even add this documentation link in the readme file. You can go and check that out. All right. And one more thing, if you remember, when we were updating the ECK bits, some pods were stuck in the pending state, right? And even after adding the new nodes, Kubernetes did not distribute the pods properly. To fix this, what we did was we reduced the discharge size to 0 and then increase it back to 3. And after that it worked, right? But later I got to know that this was an issue with the ECK bit. So when we were updating ECK bits Helm chart, the configuration changes were not getting applied. So that's the reason it was in pending state and it was still picking the old configuration. So I had to reinstall it. I did Helm uninstall and then Helm install it again, and then it started working correctly. So somehow when I was upgrading it, it was not working. So I had to uninstall and install. If you are also facing the same thing, then just remember you need to uninstall it and install it. Maybe it will be get fixed in the next version. So now everything is working fine. We can see the logs are visible in Kibana. If I go to this boutique app, and here you can see all the logs are available. You can just expand these logs and you can read about the pods, or you can read the logs messages, right? So yeah, you can see the pod name over here. If you want to see and see the logs for a specific pod, then you can definitely go to the pod and you can check that. As we set the Kubernetes namespace to boutique app, so inside that boutique app, it's giving me all the pod logs, right? So let's say I want to see the front end logs, so just add that here. Now you will be able to see all the logs from the front end pod in the boutique app namespace, right? Yeah, as you can see, given this pod name, so these all logs are available in the front end microservices, right? So this is the all logs. You can expand it here and you can see. So logs are coming from all the namespaces, and we can search and filter the logs as I showed you, and we can even create the dashboard and visualization. So this logging part is done, and you can definitely give this endpoint to the developer or the QA engineer or other guy who want to see the logs and who wants to monitor, so they can directly go to that particular link and view them. They don't need to have that access to the cluster, right? So this is the benefit of exposing the apps, right? Let's move further. I'll update the readme file for sure, but with the older version it was working. You can see even I had it here. You can see the Kubernetes namespace I had earlier as well before making this video, but somehow with the new cluster it didn't work. So I went to the documentation and I found out the solution. It's working. I'll update the readme file as well, right? So this part is done. Now let's see scaling and reliability. So we are using the microservices demo online boutique style architecture, and we have the load generator service. So here if you do kubectl get pods boutique app, we have a service called load generator. So our goal is to use the load generator to generate the traffic. We'll enable the horizontal pod autoscaler, and we'll observe the scaling behavior, and we'll validate the reliability. Let's do implement this. We'll do it step by step. So what is the load generator? Basically, as I mentioned over here in the online boutique demo, load generator continuously sends the HTTP traffic to the front end service. So first thing first, we need to install the metric server using Helm. So this is the documentation. Again, I am using the artifact hub, and I am taking that Helm chart from there and installing the metric server. So let me just add this repo quickly, and I'll install it in the kube system namespace. Let's see the pods. It's not running yet. Let's wait for some time. Alright, it is running now. Now we'll confirm that the metric server is working. So how do you confirm that? You can run kubectl top nodes or top pods. If it outputs something, then you will get to know that the metric server is working. Without metric server, the top nodes and top pods won't work. Great. We can see the CPU uses, the memory uses, right? In percentage and bytes it shows. You can even see kubectl top pods. If you want to see in a specific namespace, even that also you can mention. Alright, we are getting the usage information. So HPA means horizontal pod autoscaler. So HPA needs the CPU request is defined, then only it will work. So I think in the front end service it is already defined. You can verify it using this below command. The same command I have added in the readme file. So you can see in the front end microservices we already have the resource and limits. I mean, in the resource we have limits and requests, right? So it is already there. Now we'll create a HPA for the front end, right? So to do that, I already have it in the scaling directory. I already have the configuration YAML manifest in this directory. Yeah, the front end HPA is available. Let me explain this to you. So here the kind is set to horizontal pod autoscaler, and this is the metadata. In metadata I have name, and it will deploy in the boutique app name. And after that, in the scale target references I have given the kind as deployment and the name is front end. So basically it controls the scaling for front end deployment, right? Because we want to scale the front end microservice. So and then I have given the minimum replica is 1 and maximum is 6. So there will be always one pod running and it can scale up to 6 pods. And then the metric part. So here we are providing the metric, the type is resource and the resource name is CPU, and target we are giving the utilization, and the average utilization is set to 5. So basically this part is the CPU usage to decide the scaling, and the target CPU is 5%. If CPU is greater than 5%, then it will scale up. If it is less than 5%, then it will scale down. So scaling up will go till 6 pods and scaling down will go up to 1 pod. So the traffic flow will be when the traffic increases and the CPU usage rises up, let's say more than 5%, then this horizontal pod autoscaler, it will increase the replicas till 6 pods. If it is less than 5%, then it will decrease the replicas till 1. So if it goes more than 5%, then there will be more pods to handle the traffic. So here basically we are auto scaling based on the metric. So intentionally I kept it 5% here, which I'll explain it a bit later why I kept it 5%. Alright, let's go ahead and apply this. Let's check kubectl get hpa -n boutique app. Great, we have it here. Alright, so we saw our load generator was already running over here. Now let's increase the load. We will edit the load generator deployment. In our case, we are deploying the complete boutique app microservices through ArgoCD. As an ArgoCD application, it is deployed. If we edit it, like I'll tell you what to edit. So let me edit the deployment. To edit the deployment, you can just simply type kubectl edit deploy load generator -n boutique app. And here you have to find out the env called user, and yeah, here it is available in the template. In the spec of the containers, we have the user, and currently it is 10 users. This load generator microservice simulating 10 users to the front end, right? If we increase that, then there will be concurrent simulated users which will serve to front end, I mean which will routed to front end. So there will be concurrent simulated user. Let's say we'll make it to 100 or 200 maybe. So there will be that many users and that many requests. But if we edit it here, then the value will be overwritten because our application is deployed via Helm and it is managed by ArgoCD, and ArgoCD continuously reconciles the cluster state to match the Git, right? So if we edit it simply, then it will be overwritten. So I won't be editing it here. I'll simply exit. So what I'll do is I'll modify the value in Git, not in the cluster, because ArgoCD will detect the drift and revert it back to the Helm defined value, and that is the expect behavior in GitOps. That's why we are using ArgoCD. So I'll modify this value in Git. I'll simply duplicate it. Let me open the Helm chart. And in the values file, let me search load generator. Yeah, so here we have the load generator, and you can see there is no value exposed to that values file called user. So it should be in the template, but again if I modify the template, then I have to update the values file and I have to again package it and send it to the registry, right? Then only I can use the user from here itself. To get rid of that, to make sure I can show you how the auto scaling works, what I did is I did the average utilization is set to 5. If I set to 5, so there are already 10 users sending the concurrent request, right? So 5% is the minimum. I mean, we can set the lower number. So setting such a low value ensures that even a minimal CPU usage will exceed the threshold and HPA will get triggered and scale quick. So it becomes easy to verify that auto scaling is functioning correctly. That's the reason I kept the average utilization is set to 5, and this configuration is only for testing and demonstration purpose. This particular configuration in real production environment, the CPU threshold will be carefully tuned, right? And the scaling decision would be based on the realistic load patterns. Before that, I can show you, like if I edit it manually here, let's say I'll edit the user to 100. As we deployed this through Helm, and as an ArgoCD application, so if I change it here, it will take the change. Let's say I keep it 100 or maybe 200, and I'll save it. It says edited, but ArgoCD will revert back, because in Git we have mentioned this should be 10, and here we manually edited that. But ArgoCD will reconcile, it will take the Git as a source of truth and it will reconcile. I'll go to edit it again, so it should be 10, right? See, it is 10 now, and we can't edit that. So you have to edit it in GitHub. But in GitHub, the value is not exposed. You can definitely expose it and control it from here as well. But just to show you how the scaling works, I have kept the average utilization 5%. So even a minimal CPU usage, it will exceed the threshold, and HPA will get triggered, and it will scale quickly, right? So let's see whether it got scaled or not. kubectl get HPA -n boutique app. As you see here, the minimum is 3, maximum is 6, and now currently it has 3 replicas. Previously we had only 1 replica, now we have 3 replicas, and the CPU target is 5%, so currently we have 4%. So if we increase it more, then there will be more replicas for sure. You can definitely decrease it to 2% or 3%, then it will be more replicas over here. Let's see, there are 3 pods available or not. Yeah, as you can see here, we have 3 front-end pods. So similarly, you can also scale other services, and that's all. Congratulations. If you have made it this far and successfully deployed the application, well done. You have just completed the full hands-on implementation, and keep building this kind of projects. All right. So yeah, the additional step is cleanup. I'll show you how to clean it up. So before that, we'll just see how far we have achieved. We have that application ready. Our application is still accessible. We have the ArgoCD, right? We have Grafana, we have Prometheus exposed, and this was the whole diagram what we had initially. Let me show you the diagram once again. So this is the diagram. First we created Terraform, and through Terraform we created the whole infra. Then we made sure we are using the remote backend, and we used S3 bucket, and in Route 53 we had a hosted zone, and we use SCM for our TLS certificate, and then that is binded to our application load balancer, and our EKS is deployed, and in the private subnet we have the nodes, and AWS itself manages the control plane. Then we have our continuous integration and continuous deployment. We pushed our code to the GitHub, and here we ran GitHub action. So whenever the source code has changed, the GitHub action will get triggered. It will check out, build, it will scan through Trivy, and it will push to the GitHub container registry. And through GitHub container registry, we deployed ArgoCD image updater. ArgoCD image updater will update ArgoCD, and in the ArgoCD we deploy our application as an ArgoCD application, right? And once our application is deployed, we expose it through gateway API. We install gateway class, then gateway, then HTTP route, target group configuration, load balancer configuration, everything we have deployed inside gateway API. And then if we need any host name to be updated automatically in Route 53, we have external DNS for that, which was working. And after that, we monitored using Prometheus, Grafana, and Alertmanager, and that alert are sent to Slack. We configured Slack as well, right? And we used IRSA and pod identity agent both to configure the applications. Then after monitoring, we implemented logging stack. We ran ECK Operator, and ECK Operator is managing Elasticsearch, Kibana, and Filebeat. So Filebeat is a lightweight log zipper. It will take the logs from all the namespaces and send to Elasticsearch, and from Elasticsearch we can view the logs in Kibana, right? Then after that we saw how to scale our application based on the load, based on the metrics, and that's where we saw how HPA works, and we automatically scaled our application like front end and all, right? So this is the whole thing I have got you covered. As a user, you can access the application, as a developer or DevOps engineer, you can go to these endpoints and you can monitor the applications and all, right? So this is the whole thing. I hope you understood the project very clearly and you got to know something new. So the final step is cleanup. Let's do the cleanup. So to clean that up, what we'll do is, so first I'll edit this and I'll make it to 2, because in Terraform code I had 2 over there. If I if I make it 3 and I'll do Terraform plan, then Terraform will give me the drift, right? So to get rid of that, I'll just make it to 2, or you can change in the Terraform code as well. That is not a big deal. And then you have to delete the load balancer and the security group first in the UI, because we are not controlling that, or we are not managing that through the Terraform, isn't it? So what I'll do is, I'll go to the EC2 section and I'll delete the load balancer. If you don't delete that load balancer, then when you run Terraform destroy, this load balancer will get stuck and your VPC and all won't be get deleted, because there is already a load balancer is attached to that VPC, so it won't get deleted. So only I am deleting this load balancer manually. Delete that load balancer and confirm, and delete the security group of the load balancer as well, right? Go to the security groups. So this is the security group of the load balancer. Yeah, this is the one. Yeah, security group for load balancer, this is the one. You can just delete this as well. Delete security group. All right, so this is deleted. Great. Now we can destroy the whole cluster, Bastion host, whatever we had created using Terraform. You can just go to our local machine. So this is the Bastion host. I'll just simply go to my local machine. Yeah, this is my local machine. I'll go to the Terraform. Yeah, so here we are in the Terraform. I'll run Terraform plan just to make sure that we are not getting any drift. So I'll run Terraform plan first. So you have to run this in the local machine where you initially run Terraform to create the resources. So it's saying 3. This header block is changing, I guess. Yeah, this header block is changing. So you can ignore this for now. This is fine. We can still destroy. And what else is there? Node group. Yeah, the public IPL and all are changing. The instance ID and all are changing, but that is fine. That is fine. Yeah, these are the minor ones, right? So you can still destroy. So here in the Terraform directory, you need to run Terraform destroy. Just type yes. It will take some time to destroy the whole resources, specifically the cluster will take a bit of time to destroy. So I'll get back once it is done.
A few moments later.
So it's still destroying. So VPC destruction won't take much time. I think some of the resources is still depending on the VPC. So only Terraform is not able to destroy the VPC. Let me go to the VPC. I'll try to delete this manually over here and let me see what all the resources are still available. So I can see there is a security group. Yeah, so this security group is for load balancer. It's still there. So I'll delete it manually so that Terraform can delete the VPC quickly. So this security group, I'll delete it. Now it should be able to, yeah, as you can see, the destruction has been completed. So as you can see, the VPC got deleted. There is no cluster, and there will be no EC2 instances running. Great. So the cleanup is also done. And at last, as I told you, I have given you the step-by-step implementation, how you can push the images to GHCR and how to create the Helm package and store it in GHCR, right? So you can completely follow this readme file to deploy it. Yeah, and that's the wrap up on this complete end-to-end GitOps based DevOps project. So in this project, we didn't just deploy an application, we built a complete production grade system from scratch, right? And we covered everything from infrastructure to deployment, security, monitoring, and logging. Everything we have covered, right? And tool and services wise, we cover Terraform. We for DNS and TLS we had Route 53, and for CI/CD pipeline we use GitHub Action, and for security scanning we used Trivy in the GitHub Action, and for container registry we used GitHub Container Registry, and we used Kubernetes, and inside Kubernetes we use Helm, and for ingress and traffic management we used external DNS and gateway API, and ArgoCD and ArgoCD image updater also we used for GitOps deployment, and for monitoring and alerting we used Prometheus, Grafana, Alertmanager, and Slack, and for logging we used ECK Operator, Elasticsearch, Filebeat, and Kibana. So these all the tools we have covered. Yeah, along the way even we faced some challenges, like we got some errors, we faced some scheduling issue, we even faced some authentication problems. So we solved them step by step. It helps you learn the topics in bit depth, right? Also this project gives you a real production level understanding of DevOps, like how tools and services communicate with each other, how they integrate with each other, and you can concretely showcase this project in the interviews, and you can add this in your resume, and you can definitely implement it in your own environment, in your own AWS account. If you are doing so, then post the same in LinkedIn or wherever you want. Just tag me, I'll be happy by seeing that, and it gives me more motivation to create such content. So this is all what I wanted to say. If you found some value in this series, make sure to like, share, and subscribe to DevOps Talk for more practical DevOps related contents. See you in the next one.